Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. The story of galaxies. Cosmic cities in the night. On a clear, moonless night, far from city lights, the sky becomes an infinite ocean of darkness studded with stars. Across that darkness arches a pale, luminous band, a gauzy river of light flowing from horizon to horizon. For millennia, humans have looked up at this silvery band with wonder. In myth and legend, it became a celestial road for the gods, a river of souls, or the spilled milk of a goddess strewn across the heavens. Before our cities lit the night and banished the stars, the Milky Way was a canvas for our imagination and a mirror of our yearning. People around the world named it in their own poetic terms: a straw way dropped by heavenly farmers, a silver river bridging lovers, a sky road for migrating birds, a spirit path for departed souls. Yet, even in their enchantment, those early stargazers could not imagine the true nature of that milky band. It would take centuries to discover that every wisp of that glow comes from countless distant suns, and that beyond the Milky Way lie other cosmic cities of stars, faintly visible as tiny smudges in the sky. What are these great star cities, these galaxies, that form the grand architecture of the universe? How did we come to understand them, and what do they tell us about our own existence? Our journey begins with the story of how humanity slowly awakened to the true scale and wonder of the galaxies. From myth to discovery, the Milky Way and beyond. For most of human history, the Milky Way was a mystery. Even as ancient myths wove stories about its light, no one knew what it truly was. The breakthrough came in 1610 when Galileo Galilei turned his telescope to that milky band. What he saw astonished him. The smooth glow dissolved into countless faint stars. The Milky Way was not a cloud or the breath of gods. It was made of stars. This was our first glimpse of the galaxy's true nature. Still, the Milky Way was thought to be the entire universe, a lone island of stars in a vast, dark sea. As the centuries passed, a few bold thinkers began to suspect there might be more islands out there. In 1755, philosopher Immanuel Kant imagined that the faint cloud, like patches observed in the night sky, were actually other Milky Ways, island universes far beyond our own. In the 1800s, telescopes grew more powerful, and astronomers began to see structure in these mysterious patches. The Great Irish Telescope of Lord Rosse, for example, revealed a spiral form in the Whirlpool Nebula in 1845, a majestic pinwheel of light. Such sightings fueled speculation. Could these spiral nebulae be galaxies in their own right, colossal systems of stars as vast as the Milky Way? The idea was daring and controversial. Many scientists insisted these nebulae must be nearby clouds of gas or clusters within our Milky Way, because imagining them as separate galaxies made the universe seem unthinkably large. Meanwhile, our understanding of the Milky Way itself was growing. In 1785, William Herschel attempted to map the Milky Way by counting stars in every direction, sketching our star system as a vast, flattened disk. Later, in the early 1900s, astronomer Harlow Shapley used pulsating stars in globular clusters to measure distances across the Milky Way. He discovered that those clusters formed a great halo centered not on Earth, but far off in the direction of the constellation Sagittarius. In other words, the center of the Milky Way was nowhere near our solar system. Our sun was tucked in the suburbs, tens of thousands of light years away from the galactic center. The Milky Way, Shapley found, was enormous, on the order of 100,000 light years across or more, and our place in it was humble. Yet the true nature of the spiral nebulae still hung in the balance. Were they part of this one huge galaxy, or separate galaxies altogether. On April 26, 1920, in Washington, D.C., a crowd gathered at the Smithsonian's Museum Auditorium to hear a public debate about the scale of the universe. It was a historic showdown. Two astronomers, Harlow Shapley and Heber Curtis, argued over the scale of the universe. Shapley, armed with his measurements of the Milky Way's vast size, believed our galaxy was the only galaxy. Everything we saw, including the spiral nebulae, lay within it. Curtis, however, maintained that the nebulae were far outside our galaxy, perhaps as other galaxies unto themselves. They traded evidence before an audience, posing a profound question. Was the universe essentially one galaxy, or was our Milky Way just one of many? The answer arrived only a few years later, from the Mount Wilson Observatory in California. There, in 1923, astronomer Edwin Hubble peered through a 100th-inch telescope, then the world's largest, and examined the Andromeda Nebula in exquisite detail. Amid the hazy glow of Andromeda, he identified a faint, Cepheid variable star, a type of star that waxes and wanes in brightness in a regular rhythm. Cepheids are valuable cosmic yardsticks. Their pulse period reveals their true brightness, which in turn can be used to calculate their distance. When Hubble calculated how far away this star was, the result was staggering, roughly 2.5 million light years. Far beyond the Milky Way's boundaries, Andromeda wasn't a nearby cloud at all. It was an entire galaxy of its own. Hubble's discovery was a watershed moment. It's said that upon seeing Hubble's evidence, Shapley conceded with awe, "Here is the letter that has destroyed my universe." The paradigm had shifted. The Milky Way was no longer the entire cosmos, but one galaxy among a multitude. In one stroke, the universe became immensely larger. The Milky Way was revealed to be just one galaxy among many. In the wake of Andromeda's measured distance, other spiral nebulae were likewise found to be far outside the Milky Way. Those tiny smudges and whirlpools on photographic plates resolved into myriad galaxies, each an island of stars. Our one-island universe had become an archipelago of galaxies, scattered through an expanding cosmos. By the mid-20th century, it was clear that the universe is teeming with galaxies. Astronomers began to catalogue the galaxies by the thousands, then millions. Estimates of the total number of galaxies climbed into the billions. Edwin Hubble himself, after proving the existence of other galaxies, went on to observe that galaxies are rushing away from one another, evidence that the universe is expanding from a primordial beginning. But it all started with that realization that the Milky Way is not alone. The word galaxy, once synonymous with our Milky Way, now described an entire class of colossal star systems. The night sky's faintest whispers of light became mighty galaxies in our understanding. In the span of a few decades, humanity's view of the cosmos was transformed. We went from a universe confined to one galaxy to a universe filled with countless galaxies stretching in all directions. The revelation was as humbling as it was exhilarating. Our Milky Way, with its billions of stars, was just one among billions more. The scale of creation had expanded beyond imagination. The stage was set to explore these newfound galactic realms, to ask what galaxies are made of, how they live and die, and what role they play in the grand story of the universe. Anatomy of a galaxy, stars, dust, and dark matter. What does a galaxy actually look like, up close? Picture a giant rotating pinwheel made of stars. In a typical spiral galaxy like our Milky Way, billions of stars are arranged in a flat, pancake-shaped disk that revolves around the center. Graceful spiral arms wind outward from a bright central region like glittering trails. Those arms are not solid arms at all, but patterns, density waves, where stars and gas bunch together. They mark where new stars are being born, lighting the arms with young, blue starlight and the pink glow of nebulae. Traces of dark, filamentary dust clouds weave through the arms, silhouetting the starlight. Closer to the center of the galaxy, the spiral arms give way to a bright central bulge, a crowded spherical hub of older reddish stars. At the very heart of that bulge, in the nucleus of the galaxy, lurks a powerful presence, a supermassive black hole. This monster, millions of times the mass of the Sun, anchors the core. Most of the time, it's invisibly quiet, swallowing the occasional drifting star or gas cloud. But it's there, a dark heart at the center of the galaxy's light. Surrounding it is a dense swarm of stars in the bulge, orbiting like bees around an unseen queen. Moving outward from the bulge, we transition into the disk of the galaxy, the broad, flat region where the spiral arms sweep around. Here is where the majority of a spiral galaxy's stars reside, including our own Sun. These stars orbit the galactic center in nearly circular paths as the entire disk rotates majestically. Our Sun, for instance, takes about 230 million years to complete one circuit around the Milky Way's center. Throughout the disk, we find vast clouds of gas and dust, the raw material for new stars. In fact, the spiral arms themselves are sites where this gas and dust have been compressed, triggering the birth of clusters of stars. It's within these stellar nurseries that bright young stars form and burn hot, illuminating their surroundings. Beyond the visible disk of stars, a galaxy extends further into a much fainter realm. Enveloping the galaxy is a vast halo of old stars, globular clusters, and something even more mysterious: dark matter. Scattered throughout this halo are ancient globular clusters, each a spherical swarm of very old stars orbiting the galaxy's center. The halo's stars are scarce and dim, so you'd barely notice them in a photograph. But the halo isn't empty. It's filled with an enormous amount of invisible mass. This is the galaxy's dark matter halo, a spherical cloud of matter we cannot see, but whose gravity we can feel. It's this dark matter that provides much of the gravitational glue holding the galaxy together, extending well beyond where the starlight fades out. In a real sense, the true size of a galaxy is defined not just by its starlight, but by this huge dark halo reaching far into space. All these components, the spinning disk with its spiral arms, the central bulge and black hole, and the extended halo of stars and dark matter, together form a single coherent system bound by gravity. A galaxy is like a cosmic ecosystem. Stars are born from gas, live out their lives, and die, often exploding and enriching the galaxy with heavier elements. Those elements mix into new gas clouds, seeding the next generation of stars. Over billions of years, this cycle of birth and death gives the galaxy its character. In our Milky Way, for example, generations of stars have come and gone, forging the elements that now make up our Sun, our planet, and even our bodies. Not every galaxy has the same structure, of course. Spirals like the Milky Way have distinct disks and arms. Other galaxies, called elliptical galaxies, are shaped more like rounded or football-shaped swarms of stars with no obvious disk or arms, essentially just big, puffy collections of stars. They tend to contain older stars and little gas and dust. And then there are irregular galaxies, which defy neat classification, with chaotic shapes often caused by gravitational encounters or mergers. But all galaxies share the same basic ingredients: stars, gas, dust, and dark matter, arranged in some unified form. Whether a galaxy is a flat spiral or a blob like elliptical, it will likely have a central concentration of stars and a surrounding halo dominated by dark matter. In a way, a galaxy is like a city of stars. It has a densely populated downtown, sprawling suburbs, and distant outlying regions that fade into the darkness. It is an enormous, self-contained society of stars orbiting together through space. Our Milky Way, for instance, contains hundreds of billions of stars, each as real and potentially as sun-like as our own, along with vast interstellar clouds and invisible dark matter. Yet despite this richness, on the scale of a galaxy, space is mostly empty. Stars are so far apart that if you shrank the Milky Way to the size of an earthly city, each star would be like a single grain of sand, separated from the next grain by blocks or miles of empty space. From the central black hole to the far-flung halo, a galaxy is a complex, gravitationally bound system. Every part affects the others. The black hole can influence the surrounding bulge. Supernova explosions from dying stars enrich the gas that forms new stars, and the dark matter's gravity guides the orbits of stars in the outskirts. This grand structure, stars, dust, gas, and dark matter dancing in unison, is what makes a galaxy more than just a random collection of matter. It's a self-organizing cosmic city, one that evolves and changes over time, but remains bound together by the inexorable pull of gravity. In the next part of our journey, we will look at how astronomers classify these galactic cities by their shapes and what those shapes reveal about the galaxy's histories. Galactic diversity, spirals, ellipticals, and irregulars. Galaxies come in a dazzling variety of shapes and sizes. In the early 20th century, Edwin Hubble devised a system to classify them, often depicted as a tuning fork diagram. At one prong of the fork are the elliptical galaxies, big, smooth balls of stars ranging from nearly round to elongated ovals. On the other prong are the spiral galaxies, flat disks with spiral arms, further divided into those with a central bar of stars and those without. In between, bridging the fork's handle to the prongs, are lenticular galaxies, disk, shaped like spirals but without visible arms, appearing as a smooth lens of stars. And off the neat ends of the fork are the oddballs, irregular galaxies that don't fit any simple shape. The spiral galaxies are perhaps the most visually striking. They look like cosmic pinwheels, with curving arms and sometimes a bar through the center. Our Milky Way is one such barred spiral, as is the nearby Andromeda galaxy. Spirals tend to have plenty of gas and dust, which fuels ongoing star formation in their arms. The presence of bright young blue stars and glowing nebulae gives the arms a speckled bluish tint, while the central bulge shines yellow, white with older stars. Spirals can have arms that are tightly wound or loosely trailing, and a given galaxy might have two prominent arms, or multiple fragmented ones. Despite these differences, when you see that classic spiral form, you're looking at a galaxy that is actively creating stars and has a dynamic, rotating disk. Elliptical galaxies, by contrast, are more like cosmic rugby balls or giant glowing halos. They lack the clear features of spirals, no arms, no disk, just a broad ellipsoid of stars. Some ellipticals are nearly spherical, others are stretched and elongated. These galaxies typically appear reddish or yellowish because they are dominated by older, cooler stars. Very little cold gas or dust remains in an elliptical, which means new stars are no longer forming there. Instead, an elliptical galaxy is a more quiescent system, a retired galaxy in terms of starbirth. Many ellipticals are also enormous. Some of the largest galaxies in the universe are giant ellipticals like M87 in the Virgo cluster, a monster galaxy with trillions of stars and a supermassive black hole at its core. These leviathans often sit in the cores of galaxy clusters, having grown by gobbling up smaller galaxies over time. Sitting between spirals and ellipticals are the lenticular galaxies. A lenticular galaxy has a central bulge and a disk like a spiral, but no spiral arms. It's as if the whirlpool pattern of a spiral galaxy has faded away, leaving just a smooth disk. Lenticulars often have used up or lost much of their gas, so they have little ongoing star formation, similar to ellipticals in that sense. Yet they still retain a flattened disk structure of stars. They might represent a transitional phase, perhaps a spiral galaxy that lost its gas, or maybe the product of mergers that didn't completely randomize the stars into a puffball. They tend to have older stars like ellipticals, and without arms they look more featureless, just a bright core, and a faint disk fading outwards. Then there are irregular galaxies, which, as the name implies, refuse to be neatly categorized. Irregulars have ragged, blobby shapes with neither arms nor smooth symmetry. Many are small dwarf galaxies that simply don't have enough mass to form an organized structure. They might look like clumps of stars and gas without a clear center. Others have been distorted by gravitational encounters. A past close pass or collision with another galaxy may have torn them into chaotic shapes. The large and small Magellanic Clouds, companion galaxies to the Milky Way visible in the southern hemisphere's night sky, are classic examples of irregular galaxies. They are full of active star formation and nebulas, but lack the symmetry of a spiral. Irregulars remind us that not every galaxy is a majestic pinwheel or a serene ellipse. Some are cosmic train wrecks or nascent fragments still finding their form. These shapes aren't just cosmetic. They tell a story about a galaxy's history and life cycle. A spiral galaxy's supply of gas and abundance of young stars suggests it's in an active phase, still evolving gradually and relatively undisturbed. An elliptical galaxy, full of old stars and little gas, likely has experienced a more violent past. In fact, astronomers believe that many ellipticals are the result of galactic mergers. When two spiral galaxies collide and merge, the immense gravitational chaos can scramble their disk structures and trigger bursts of star formation that eventually use up the gas. The end product is often an elliptical galaxy, a big ball of stars that used to be two separate spirals. In the dense environments of galaxy clusters, where collisions are more frequent, we see many ellipticals, hinting at this violent upbringing. Lenticular galaxies might tell another evolutionary tale, perhaps a spiral that slowly lost its spiral arms. Imagine a spiral galaxy that falls into a cluster of galaxies. As it plows through the hot gas in the cluster, it can be stripped of its own gas. With its star, forming fuel removed, its arms would fade and cease to be obvious. What remains would be a lenticular, a disk of mostly older stars, quietly flying on without the youthful sparkle of arms. Thus, a galaxy can morph from a star, forming spiral into a more passive lenticular if the conditions take away its gas. Over time, even that disk might puff up through minor collisions or dynamic interactions, potentially becoming more elliptical. Irregular galaxies often represent youth or disruption. Some could be young galaxies that haven't settled down. In the early universe, many galaxies were clumpy and irregular before they coalesced into spirals or ellipticals. Others are simply what happens when galaxies gravitationally torment each other. An otherwise normal spiral can be twisted out of shape by a close pass with another galaxy, becoming irregular in the aftermath. In that sense, irregulars sometimes are like the before and after snapshots of galactic evolution, the building blocks that will later form larger galaxies, or the mangled remnants after a collision. Galactic morphology is a bit like a family album of galaxies. Spirals with their youthful star, forming glow, ellipticals with the faded glimmer of old age, and lenticulars and irregulars as the in-betweens and outliers. By classifying galaxies, astronomers glean insight into how galaxies live and change. We see that galaxies are not static. They can transform. Graceful spirals can merge and swell into giant ellipticals. Small dwarfs can be cannibalized by bigger galaxies. Collisions can shatter a galaxy's symmetry or spark new stars. The shape we observe is a snapshot of a galaxy's ongoing story. This diversity in form is a testament to the myriad paths galactic evolution can take. It reminds us that each galaxy we see in the telescope, whether a perfect spiral or an amorphous smudge, has a unique history written in its shape and stars. Understanding these classifications and what they imply sets the stage for exploring how galaxies are born, grow, and sometimes die, a story that begins in the aftermath of the Big Bang and continues to unfold across cosmic time. Origins and evolution. from the Big Bang to today. Galaxies have not always filled the universe. There was a time, shortly after the Big Bang, when no galaxies existed at all, no stars, no structures, just a hot, dense fog of energy and subatomic particles. But even in that primordial chaos, tiny ripples in density were present. As the universe expanded and cooled, these slight fluctuations, quantum wrinkles stretched to cosmic scales, became the seeds of all future structure. Gravity began to amplify them. Regions just a bit denser than average slowly pulled in more matter. In the earliest epochs, matter in the universe was mostly hydrogen and helium gas, along with a much larger share of invisible dark matter. Dark matter doesn't interact with light, so as the universe cooled, it was free to clump together quickly, unhindered by radiation pressure. It formed an invisible scaffolding, a cosmic web of filaments and knots, into which ordinary gas flowed. Within a few 100 million years after the Big Bang, some of these knots of dark matter and gas had grown dense enough to ignite the first stars. These stars, we call them population 3 stars, were unlike any that exist today. They were likely extremely massive, bright, and short-lived, made of pristine hydrogen and helium. They lived fast and died young, some exploding as supernovae that enriched their surroundings with the first heavier elements like carbon, oxygen, and iron. With the birth of the first stars, the first proto-galaxies emerged. They might not have looked like the grand galaxies we see now. More likely, they were small, clumpy collections of stars. Perhaps only thousands or millions of stars bound together. But they were the seeds of future galaxies. Over the next few 100 million years, these fledgling star clusters began to merge and gather. Gravity drew proto-galaxies toward each other, combining them into larger structures. By 1 billion years after the Big Bang, the universe was becoming a cosmic cityscape of early galaxies. Many of them were irregular and turbulent, actively forming stars at a ferocious rate. The ultraviolet light from these newborn galaxies helped end the cosmic dark ages by reionizing the hydrogen gas in intergalactic space, making the universe transparent to starlight. As time went on, small galaxies merged into larger ones in a hierarchical fashion, like streams converging into rivers. This process of hierarchical merging meant that big galaxies grew at the expense of smaller ones. Every merger was a dramatic event. When two galaxies collided, their stars typically passed by each other, but their clouds of gas slammed together, triggering bursts of new star formation. The merging galaxies' shapes distorted, sometimes coalescing into a new form. Through countless such mergers and acquisitions, galaxies kept growing. A large galaxy like our Milky Way likely assembled from the amalgamation of many smaller progenitors over billions of years, each merger adding to its mass and mixing up its stars. Meanwhile, galaxies also grew by a quieter method, accretion of gas from their surroundings. Along the filaments of the cosmic web, tendrils of gas continued to funnel into galaxies, especially in the early universe. This fresh gas was fuel. It settled into rotating disks and kept star formation alive. In fact, even as major mergers built up the bulk of galaxies, a steady flow of intergalactic gas helped form extended disks and spiral structures. In galaxies that didn't undergo disruptive collisions for a long stretch, well, ordered disks had time to develop, the kind we see in majestic spiral galaxies. The Milky Way, for instance, has likely enjoyed a relatively quiet life for the past several billion years, allowing it to maintain its spiral disk and keep forming new stars at a modest rate by accreting gas. Galaxies also evolve internally. As generations of stars live and die within them, the galaxy's content changes. Early stars forged new elements and spread them out when they died, gradually enriching the galaxy's gas with heavier elements. This means later generations of stars, like our Sun, were born from material that had been recycled through previous stars, including elements crucial for planets and life. Over billions of years, the rate of star formation in the universe rose to a peak and then declined. That cosmic high noon, when galaxies were churning out stars at record pace, is long past. Many galaxies today are less active, having used up or lost much of their star-forming fuel. The environment around a galaxy plays a big role in how it evolves. A galaxy, floating relatively alone, might keep its gas and continue forming stars for a very long time. But a galaxy in a crowded cluster can have a much harsher life. As it plunges through the thin, hot plasma that fills galaxy clusters, its own gas can be stripped away like leaves torn off a moving car. With its gas gone, its star formation can slow to a halt, turning a once blue spiral into a gas, poor lenticular or elliptical over time. Also, frequent interactions in a cluster, small gravitational tugs from many neighbors, can stir up a galaxy's structure, making spiral arms disheveled or triggering periodic bursts of star formation until the gas is exhausted. Throughout cosmic time, mergers big and small continued to shape galaxies. Two sizable galaxies merging can transform their structures, often yielding an elliptical galaxy and perhaps fueling a quasar as their central black holes ignite. Minor mergers, where a big galaxy cannibalizes a smaller one, are common too. Our Milky Way is in the process of digesting several dwarf galaxies even now, their stars forming streams in our halo. Every such event adds stars to the larger galaxy and can jostle its structure slightly. Galactic evolution is thus a complex tapestry woven from smooth flows of gas, violent collisions, internal fireworks of star birth and death, and environmental influences from the cosmic neighborhood. Over 13.8 billion years, galaxies have grown from tiny embryonic fluctuations into the grand systems we see today. Many started as little more than glimmering irregular clumps. Some settled into stable rotating disks. Others underwent repeated smash-ups that left them as giant ellipticals. Some, especially smaller ones, remain irregular to this day, perhaps never having the chance to form a tidy structure. One intriguing aspect of galaxy evolution is the co-evolution of galaxies with their central black holes. Almost every large galaxy has a supermassive black hole in its core, and somehow these black holes grew in tandem with their galaxies. In the early universe, frequent mergers and copious gas likely fed the black holes, turning some into blazing quasars. There's a curious correlation today. The mass of a galaxy's central black hole closely relates to the mass of the galaxy's bulge of stars, hinting that galaxies and black holes regulated each other's growth. It's a bit of a chicken or egg problem. Did big galaxies form first and then their black holes? Or did black holes form and help shape galaxies? But evidence suggests an intricate feedback dance. For example, a quasar can unleash so much energy that it blows gas out of the host galaxy, quenching further star formation for a time. Thus, the evolution of a galaxy is tied not only to external events, but also to the sometimes fierce influence of its own central engine. From the primordial gas collapsing into the first star clusters, to the grand collisions that built up cluster giants, galaxy evolution spans the entire history of the universe. It's still ongoing. Even now, galaxies continue to interact and grow. Our local group of galaxies is quiet at the moment, but the Milky Way and Andromeda are drifting inexorably closer and will merge billions of years from now, reshaping into a new, larger galaxy. Eventually, as eons pass, galaxies will use up much of their gas and star formation will slow to a trickle. The night skies of the far future may be dominated by aging red stars and fading galaxies. But for now, in this epoch, galaxies of all types still populate the cosmos, from lively spirals to sleepy ellipticals, each a product of the rich evolutionary journey that took it from the aftermath of the Big Bang to the form we observe today. When galaxies collide, cosmic encounters and mergers. Galaxies are not static, isolated islands. They often interact and sometimes collide in a slow motion dance governed by gravity. Imagine two enormous cities drifting toward each other over eons. As the galaxies draw near, their mutual gravity stretches and warps them. Long tidal tails of stars are drawn out, and great arcs of gas are flung into intergalactic space. If we could watch this unfold, we'd see the two galaxies distort like taffy being pulled, perhaps looping around each other once or twice. Over hundreds of millions of years, they may sway back and forth in a gravitational embrace before eventually merging into one. Despite the word collision, individual stars almost never hit head-on during these encounters. The distances between stars are just too vast. The galaxies pass through each other like ghosts, but gravitational forces wreak havoc on their structures. The delicate spiral arms of a spiral galaxy can be torn apart or twisted into new shapes. In some cases, a smaller galaxy plunging through a larger one can spark a graceful ring galaxy like a ripple in a pond. In other cases, two spiral galaxies entangle, throwing out twin tidal tails of stars. The colliding antennae galaxies are a beautiful real example, their long filaments of stars and gas arcing out like insect antennae as their disks intersect. Within the antennae, telescopes see countless young star clusters ignited by the collision. It's a glimpse of what our own Milky Way might undergo in its future encounters. One of the most dramatic effects of a galactic collision is on the galaxy's gas. When galaxies collide, their vast clouds of gas slam into each other. Unlike stars, gas clouds do collide, compressing violently. This compression can ignite a starburst, a sudden surge of star formation. In the aftermath of a collision, the merging galaxies may glow with the light of countless newborn stars, a fireworks show that can outshine a normal galaxy. The antennae galaxies, for instance, are experiencing such a burst of star birth as they merge, with brilliant clusters of young stars lighting up the wreckage. In addition, as the two galaxies coalesce, their central supermassive black holes will eventually spiral toward each other and merge as well, potentially releasing a burst of gravitational waves. Over time, the result of a major merger is often a single, more massive galaxy. Two spiral galaxies colliding will likely settle into an elliptical galaxy, their orderly disks destroyed, their gas largely converted into stars or expelled, leaving a big ball of stars. The chaos of the merger tends to randomize the orbits of stars, which is why the end product has that puffy, elliptical shape rather than a flat disk. We see evidence of past mergers in some galaxies today. Giant ellipticals often have faint shells or ripple patterns of stars around them, the ghostly remains of smaller galaxies they absorbed. Our own Milky Way shows signs of past minor mergers too. Streams of stars in the halo mark where dwarf galaxies were torn apart and assimilated. Even small interactions can leave lasting impressions. A flyby of a smaller galaxy might induce spiral arms or bars in a larger galaxy, or cause a burst of star formation by jostling its gas. Galaxies can also cannibalize their companions. A big galaxy like the Milky Way can slowly consume a small satellite galaxy, pulling it apart over billions of years. In fact, the Milky Way is doing this right now to at least two known dwarfs, their stars being strung out into lengthy loops around our galaxy as they are assimilated. These minor mergers are gentler than a head-on collision of equals, but they still contribute to a galaxy's growth and can subtly disturb its structure. One collision in particular stands out to us because it lies in our future. The anticipated encounter between the Milky Way and the Andromeda Galaxy. Andromeda, currently about 2.5 million light-years away, is on a slow collision course with us, due to meet our Milky Way in about 4 billion years. Though that sounds comfortably far off, in cosmic terms, both galaxies are essentially fated to merge. What will this titanic meeting be like? As Andromeda nears, by about 3.75 billion years from now, it will loom huge in Earth's sky, likely visible in daytime, a swirling disk of billions of stars that begins to distort the Milky Way with its tidal pull. Eventually, the disks of the two galaxies will begin to interpenetrate. Stars from Andromeda and stars from the Milky Way will sweep past one another like intermingling bees. The night sky would become a twisted, kaleidoscopic panorama of disrupted star streams, nebula set alight by shockwaves, and new star clusters forming in droves. According to simulations, the Milky Way and Andromeda will likely pass through each other once, then maybe swing around and merge fully by around 6 or 7 billion years from now. During the interaction, our solar system is unlikely to collide with another star, but its orbit around the Milky Way could be drastically altered. It might be flung into a new region of the merged galaxy, perhaps much farther from the core than it is today. By the end of the merger, the orderly spiral patterns of both galaxies will be gone. Instead, we would find ourselves in a large, amorphous, elliptical galaxy, sometimes nicknamed Milkomeda. The merged galaxy will have a new identity, containing most of the stars from both the Milky Way and Andromeda, now sharing a common cloud of stars. Though this sounds catastrophic, it's worth noting that for any beings on individual stars, the chance of a direct stellar collision or disruption is very low. They might hardly notice the gravitational collision aside from a gradually changing night sky. The real violence is in the gas and the overall structure, and indeed, if humanity's far descendants are around, they might witness a sky ablaze with more stars and nebulae than ever as the collision triggers star formation. It would be an awe-inspiring spectacle. Galactic collisions are a crucial part of the life cycle of galaxies. Through them, galaxies grow and change form. They can rejuvenate a galaxy by kick, starting starbirth, or they can quench a galaxy by using up and ejecting star, forming fuel. They create some of the most stunning vistas in the universe, luminous tails, rings, and collisional remnants that we observe with our telescopes as snapshots of different stages of this cosmic dance. In the grand scheme, collisions are also how we got from the small primitive galaxies of the early universe to the large galaxies of today. The Milky Way. Andromeda collision will be just one of countless such events that have happened throughout cosmic history and will continue to happen as time marches on. Even as the universe expands and distant galaxies recede from each other, gravitationally bound groups like our local group will eventually coalesce. The end result, far in the future, might be giant combined galaxies, each isolated in an ever-expanding void. For now, we can look at interacting galaxies elsewhere in the cosmos to understand our own galaxy's fate and the dramatic transformations collisions bring. Next, we zoom in on one of the most beautiful outcomes of galactic evolution, the process by which galaxies give birth to new stars. Whether in the wake of collisions or in the calm spiral arms, star formation is the ongoing heartbeat of a galaxy, and it's to these cosmic nurseries that we turn. The alchemy of stars, galactic nurseries, and stellar birth. Every star, including our sun, was born in a cosmic nursery, a great cloud of gas and dust within a galaxy. These nurseries, known as molecular clouds, are cold, dense patches of the interstellar medium. A typical molecular cloud might contain thousands to millions of times the mass of the sun in gas, spread over dozens or hundreds of light years. Within these dark, frigid clouds, gravity quietly begins its work. Small random density enhancements grow as gas clumps together. If a region becomes dense enough, its own gravity causes it to collapse inward. As it collapses, it fragments into smaller pockets, like a lump of dough breaking into pieces, each destined to form one or a few stars. Deep inside one of these collapsing clumps, the material compresses and heats up. A protostar takes shape, a hot, dense core of gas that isn't a true star yet, but is on its way. As the protostar gains mass from the infalling cloud, its core grows hotter and more pressurized. Eventually, when the temperature and pressure skyrocket enough, hydrogen nuclei begin to fuse into helium. This ignites the nuclear fire at the protostar's center E, and a star is born. The newfound star's radiation and stellar winds then push away the remaining shroud of gas around it, often creating a beautiful glowing nebula as the gas is ionized. What was once an opaque dark cloud now becomes a stellar nursery, lit up by its offspring. Stars tend to be born in batches. A single collapsing cloud can give birth to a whole cluster of stars, some hefty and bright, some smaller and dim. For example, peer into the Orion Nebula, a stellar nursery about 1/300 light years away. You'll see a glowing cavern of gas and dust lit by a clutch of brilliant newborn stars. Within that nebula, dozens more protostars hide in cocoons, still gathering mass. It's a snapshot of starbirth in action, a miniature version of the process unfolding countless times across our galaxy. The trapezium cluster of massive young stars at Orion's heart is carving a cavity in the cloud with intense ultraviolet light and stellar winds. Within such clusters, the most massive stars blaze to life first. Their intense radiation and powerful winds carve cavities in the cloud and can trigger further collapse in nearby parts of the cloud. In this way, massive stars can act both as catalysts and inhibitors for the next generation of stars. They are short-lived, however, living only a few million years. And when they die as supernovae, they send shockwaves through the cloud that can compress it in places and disperse it in others. In a spiral galaxy, these processes are not happening randomly everywhere, but often concentrated in the spiral arms. The spiral arms are like traffic jams in the galaxy's disk. They are regions where gas clouds get squeezed as they orbit the galactic center. When a molecular cloud enters the denser environment of an arm, it can trigger collapse and star formation. As a result, we see bright young star clusters and HII regions lining the spiral arms, marking the locations of recent star birth. These newborn stars, especially the hot blue ones, shine brilliantly but burn out quickly, so they don't drift far from their birthplaces. Hence, the arms remain defined by these ongoing nurseries. Meanwhile, older stars have had time to move away, so between the arms we mostly find middle-aged and old stars. Different galaxies have different personalities in terms of star formation. Our Milky Way currently forms only a few solar masses worth of new stars each year, quietly and steadily. In contrast, some galaxies, especially those experiencing interactions or mergers, can undergo starbursts where dozens or even hundreds of solar masses of stars form per year. These starburst galaxies are ablaze with massive young stars, and they radiate strongly in infrared as dust in the galaxies is heated by the intense stellar newborns. Irregular dwarf galaxies can also have phases of rapid star formation, often triggered by a brush with a larger neighbor or by a fresh influx of gas. On the flip side, galaxies that have lost or exhausted their gas have virtually no new stars forming. Their stellar populations are aging without rejuvenation. Star formation is a feedback loop within a galaxy. When stars form, especially massive ones, they alter their environment dramatically. The combined effect of many massive stars in a region, through stellar winds, supernova explosions, and radiation, can create superbubbles that blow holes in the galactic gas disk, venting material out into the halo. Some of that gas may cool and rain back down to the disk later, potentially forming new clouds. Or it may escape the galaxy entirely if driven hard enough, especially in a starburst or quasar phase, an event that can effectively shut down future star formation by removing fuel. In moderate amounts, though, feedback from stars helps to regulate the pace of star formation, preventing the galaxy from turning all its gas into stars at once. Over the life of a galaxy, star formation acts as a clock and a forge. It's a clock because the rate at which gas turns into stars will determine how long a galaxy's star, forming era lasts. A galaxy with a slow rate can keep making stars for tens of billions of years, while one with a rapid rate might use up its gas in only a few billion. It's a forge because each generation of stars produces heavier elements in their cores and in supernovae. Those elements get mixed into the galactic gas reservoir. Thus, the composition of the gas slowly changes. The galaxy becomes more metal-rich over time, which influences things like planet formation around new stars. In fact, our own existence is tied to this cosmic alchemy. The carbon in our cells, the calcium in our bones, the iron in our blood were all formed in previous generations of stars and scattered into the interstellar medium, eventually coalescing into the Sun and Earth. Galaxies, by forming stars, gradually enrich the cosmos with the ingredients for planets and life. Within galaxies, different environments yield different kinds of star formation. In the dense heart of a starburst or the core of a merging galaxy, star formation might be so rampant that hundreds of thousands of massive stars form in a short time, leading to an outbreak of supernovae, like a cosmic storm. In the quiet outskirts of a spiral galaxy, small clouds might occasionally birth only low, mass stars, faint red dwarfs that will live for trillions of years. Some galaxies, like large spirals, have a mix of environments, busy spiral arms and calmer inter-arm spaces, creating a balance of star formation across various scales. Other galaxies, like ellipticals, are essentially retired, containing gas that's too hot or diffuse to collapse, so star formation is dormant. From a bird's eye perspective of a galaxy, you would see star formation as twinkling patches of light. Here, a cluster of blue newborn stars. There a glowing nebula around an emerging cluster. If you could watch in accelerated time, you'd see clouds collapse and ignite, and perhaps, after a few million years, see bubbles and blasts from supernovae shaping the surroundings. It's an endless cycle. Galaxies are constantly converting some portion of their gas into stars, which then live out their lives and return some material back to the galaxy when they die. This ongoing stellar production line is the engine that keeps a galaxy visible and vibrant. It is literally the act of galaxy building, assembling new stellar components that, for a time, light up the galaxy from within. In sum, star formation is the beating heart of a galaxy's evolution. As long as a galaxy has gas, it can give birth to stars and thus continue the cosmic story, lighting up the darkness, forging new elements, and providing the raw material for planets and potentially life. Next, we explore an enigmatic ingredient that heavily influences all these processes, yet reveals itself only through gravity: the dark matter that surrounds galaxies and shapes their fate. The hidden mass, dark matter's grip on galaxies. Galaxies are not just made of stars and gas. They are enveloped by something immense and invisible that we call dark matter. This dark matter doesn't emit light, doesn't shine or obscure like dust. It interacts with ordinary matter only through gravity, yet it profoundly influences the behavior and fate of galaxies. In fact, most of the mass in a typical galaxy is dark matter, outweighing the visible stars and gas by a factor of 5 or more. It's the hidden scaffold that holds galaxies together and connects them in the cosmic web. The first hints of dark matter's presence came from observations that didn't add up. In the 1930s, the eccentric Swiss astronomer Fritz Zwicky first proposed the existence of dark matter in 1933 after observing the motions of galaxies in the Coma cluster. He calculated that the visible galaxies didn't have nearly enough gravity to hold the cluster together. Zwicky, in his blunt style, invoked a mysterious dunkel materia, or dark matter, to explain the discrepancy. His idea was ahead of its time. It was largely dismissed or forgotten for decades. Later, in the 1970s, astronomer Vera Rubin and her colleague Kent Ford made a landmark discovery after many meticulous nights at the telescope. They measured the rotation curves of spiral galaxies, essentially how fast stars and gas orbit at different distances from the galaxy's center. In a whirlpool like the solar system, we expect objects farther out to orbit more slowly because the gravity of the central mass gets weaker with distance. But Rubin found, to her astonishment, that in spiral galaxy after galaxy, the stars in the outer disks were orbiting just as fast as stars near the center. The rotation curves were flat. The expected drop off never came. This was a startling clue. If the only mass in the galaxy were the stars, gas, and dust we can see, the outer stars should not have enough gravitational pull to stay bound at such high speeds. They should drift away into space. The fact that they remain orbiting at high speed means there must be a lot of unseen mass extending well beyond the visible edge of the galaxy, creating a strong gravitational pull. The simplest explanation: an extensive halo of dark matter envelops the galaxy. This halo, roughly spherical, contains most of the galaxy's mass, though it emits no light. The stars in the outer disk are effectively orbiting within this massive invisible halo, which keeps them tethered. Dark matter halos are thought to extend far beyond the luminous parts of galaxies. For example, while the Milky Way's visible disk is about 100,000 light-years across, its dark matter halo may span 600,000 light-years or more. If we could see it, our galaxy's halo might look like a giant sphere, much larger than the Milky Way's starlit spiral, gently fading into the intergalactic medium. Every galaxy sits within such a halo, from large spirals to tiny dwarfs. In small dwarf galaxies, in fact, the dark matter's grip is often even more dominant. These little galaxies might have relatively few stars, but still plenty of dark matter, which is the only thing holding their sparse stars together. Dark matter's influence goes beyond keeping galaxies intact. It played a crucial role in galaxy formation. As described earlier, dark matter clumped into filaments and halos in the early universe, and ordinary gas fell into those gravitational wells to form galaxies. The cosmic web of large-scale structure, the immense network of galaxy clusters and filaments spanning hundreds of millions of light-years, is essentially the imprint of dark matter's distribution, with galaxies lighting up the densest spots. Without dark matter, our theories struggle to explain how the universe's structure could have formed as quickly as it did. Dark matter, being pressure, less unable to clump early, seeded galaxy formation long before normal matter could do so. Within individual galaxies, dark matter also affects their dynamics and evolution. The presence of a massive halo can stabilize a rotating disk against certain instabilities. It provides an extra gravitational well that can funnel gas towards the center or help sustain spiral density waves. When galaxies collide and merge, their dark matter halos pass through each other and overlap, adding together to form an even bigger halo around the new merged galaxy. In cluster environments, the combined dark matter of the cluster forms a deep gravitational well that can trap galaxies and super-hot gas. One of the most striking pieces of evidence for dark matter comes from images of gravitational lensing. According to Einstein's general relativity, mass bends space and thus bends light. In some massive clusters of galaxies, we see distorted, smeared images of far background galaxies, as if viewed through a funhouse mirror. These distortions allow astronomers to map the mass in the cluster. The maps show that there's far more mass than what we can see in stars and gas. A famous example is the Bullet Cluster, two colliding clusters of galaxies. In the aftermath, the X-ray emitting hot gas from each cluster was slowed and left behind at the collision center, whereas the galaxies flew on. Gravitational lensing revealed that the main mass of the clusters moved ahead with the galaxies, not with the gas, implying that the mass is dominated by something that did not collide and slow down like the gas did. This observation is a stunning confirmation that dark matter is a real physical component, separate from normal gas. Even with all this evidence, What dark matter actually is remains one of the greatest mysteries in science. We know it's there. We map its distribution. We see its gravitational effects everywhere, from the rotation of tiny dwarf galaxies to the expansion of the universe as a whole. The leading idea is that dark matter consists of some new kind of subatomic particle that doesn't interact with light, perhaps a type of particle left over from the Big Bang that swarms around galaxies. Physicists have given these hypothetical particles names like WIMPs or axions. Huge experiments deep underground and in space are attempting to detect a stray dark matter particle, and powerful colliders like the Large Hadron Collider search for hints of them. So far, dark matter particles have eluded direct detection, adding to their mystique. What we do know is that without dark matter, galaxies as we understand them wouldn't exist. Galaxies would not have formed in the same way, and those that did might not hold together. Dark matter's gravity is the glue keeping the grand design of a spiral galaxy intact and the engine that assembled galaxies in the first place. It ties entire clusters of galaxies into bound communities and delineates the cosmic web on the largest scales. In essence, dark matter is the invisible stage on which the luminous drama of stars and galaxies unfolds. We find ourselves living inside this invisible halo, unaware of its particles as they stream through us, yet deeply dependent on their gravitational presence for our very existence in a galaxy. Understanding dark matter is crucial to fully knowing galaxies, their rotation, their shape, their past, and their future. As our story of galaxies continues, we turn our attention back to the visible centers of these systems, in particular to the monsters lurking there. In the cores of galaxies, including our own, lie supermassive black holes that, when awakened, can blaze forth as active galactic nuclei and quasars, outshining entire galaxies. These extreme objects are another key piece of the galactic puzzle. Galactic beacons, quasars, and active nuclei. In the heart of almost every large galaxy lies a supermassive black hole, a gravitational titan millions or billions of times the mass of the Sun. Most of the time, these black holes are quiet, lurking in the darkness as stars and gas orbit innocently around them. But when a black hole feeds, a galaxy can transform. Matter swirling into a hungry black hole releases astonishing energy, enough to outshine the entire galaxy. The nucleus of the galaxy blazes with light, and we call it an active galactic nucleus. When an AGN is extremely luminous, especially seen in the distant universe, we often use the term quasar. A quasar is essentially a hyperactive galactic core E, a supermassive black hole gorging on infalling gas and shining like a beacon across the cosmos. How does a black hole, which by itself emits no light, produce such brilliance? The key is the accretion disk, a swirling disk of gas and dust that forms around the black hole as material falls in. As matter spirals inward, immense gravitational and frictional forces heat the disk to incredible temperatures, millions of degrees. The disk begins to glow fiercely in X-rays, ultraviolet, and visible light. Gas closer in moves at relativistic speeds, magnetic fields twist through the disk, and often the black holes spin and magnetic forces channel some of the inflowing material into twin jets that shoot out along the black hole's poles. These jets are streams of charged particles accelerated to nearly the speed of light, blasting out of the galaxy's core into space. They can extend thousands or even millions of light years, creating radio, emitting lobes far outside the galaxy. To an observer from afar, a galaxy with an active nucleus might appear as a bright star, like point at its center, or even completely outshine the galaxy's entire starlight. Quasars in the distant universe appear as brilliant beacons on the sky, some of the brightest individual objects known. For instance, a typical quasar can emit hundreds or thousands of times more light than a normal galaxy containing 100 billion stars. And all that energy comes from a region no larger than our solar system, the area right around the black hole. It's as if a flashlight the size of a pinhead outshone a lighthouse. That's the power of a feeding supermassive black hole. Quasars were first identified in the 1960s as puzzling sources of radio waves and faint star-like optical counterparts with strange emission lines. When astronomer Martin Schmidt realized those lines were highly redshifted hydrogen, it meant these objects were incredibly distant, yet astonishingly bright. This was the first clue that quasars were not stars in our own galaxy, but something far more powerful in the distant universe. We now know thousands of quasars, and we interpret them as galaxies in an active phase. Their central black holes are accreting matter at a high rate. Quasars were more common in the early universe, which makes sense. Back then, galaxies had more gas in their centers and were colliding more frequently, providing ample fuel for black holes. Many quasars lived during that cosmic era when galaxies were growing and merging. Today, with less fuel available, most big galaxies have quiescent black holes. Our Milky Way's central black hole, for example, is currently a feeble glimmer by quasar standards. It occasionally snaps up a passing chunk of material, producing a flicker of X-rays, but nothing like a continuous blaze. Active galactic nuclei come in a menagerie of types: quasars, blazars, Seyfert galaxies, radio galaxies, which largely reflect different viewing angles and power levels of the same basic phenomenon. If we look directly down the barrel of a jet, we see a blazar. If the active nucleus is powerful, but we see it at an angle where the galaxy's dust obscures some light, we might categorize it as a radio galaxy or a type of Seyfert galaxy. But all these are AGNs, central engines powered by accretion onto supermassive black holes. The effects of a quasar or AGN on its host galaxy are profound. The radiation and winds from the active nucleus can blast apart or heat the gas in the galaxy's core. A vigorous quasar can effectively quench star formation in its host by blowing away or heating the cold gas. This means that a galaxy's active heart can govern its own growth, a kind of self-regulating mechanism. If too much gas piles into the center, the black hole lights up, the quasar blows out gas, and the galaxy's star, forming future, is altered. This feedback might explain why we observe the tight correlation between black hole mass and the bulge mass of galaxies. They grew in tandem, each affecting the other. Observationally, an active galaxy can look quite spectacular. Some galaxies have bright cores and jet structures visible in radio or optical images. In images from Hubble or James Webb, we sometimes see quasars with faint galactic hosts around them, or pairs of interacting galaxies where one nucleus is lit up, possibly triggered by the interaction. When we peer into the distant universe, almost every speck of light in the Hubble ultra-deep field that isn't a star in our Milky Way is a quasar shining from an era long ago. The existence of quasars tells us that galaxies and their black holes are intimately connected. A galaxy might spend a small fraction of its life as a quasar, but during that time, it can have an outsized influence on its surroundings and be visible clear across the universe. In a sense, quasars are cosmic lighthouses, marking where massive black holes dine. They allow us to study galaxies in the making, as many quasars are seen in young, formative galaxies undergoing collisions or rapid growth. They also serve as backlights. We can study the gas in the space between galaxies by looking at how quasar light filters through it. Our Milky Way's black hole might one day gulp enough material to become more active, though it likely would never rival the brightest quasars from the universe's youth. Still, even a modest AGN can produce spectacular phenomena like X-ray flares or relativistic jets. The center of our galaxy shows evidence of past active episodes, gigantic bubble structures emanating from the core, perhaps from an AGN flare a few million years ago. In the grand tapestry of galactic life, quasars represent a youthful exuberance, a time when a galaxy's central engine can dominate its light output. They are a phase that many galaxies likely went through. Today, by studying both gentle galaxies and those with raging quasars, we get a complete picture of galactic evolution. We see a galaxy's quiet, star, forming suburbs, and also its volatile, energetic core when it turns on. With the phenomenon of AGN understood, we can now appreciate that a galaxy is not just a collection of stars drifting passively. It has a central heart that can beat furiously when fed. Having explored the brilliant hearts of galaxies, we now step back out to consider something smaller, yet still crucial to the galactic story. The dwarf galaxies that swarm around larger ones and fill the universe. These diminutive galaxies may be tiny, but they carry clues about how galaxies form and about the mysterious dark matter, making them far more important than their size suggests. Little brothers, dwarf galaxies and galactic satellites. Surrounding every large galaxy are smaller satellite galaxies, dwarf galaxies, the diminutive companions that populate the universe in huge numbers. Dwarf galaxies are tiny by galactic standards, perhaps only a few thousand light years across or less, containing as few as a few million stars. They come in various flavors. Some are irregular clumps with ongoing star formation. Others are diffuse spheroids of old stars. Though they may seem insignificant next to a giant spiral or elliptical, these little galaxies play an outsized role in the story of cosmic evolution. In our own cosmic neighborhood, the Milky Way has dozens of known dwarf satellites. The two most famous are the large and small Magellanic Clouds, irregular dwarf galaxies visible to the naked eye in the southern hemisphere. These clouds are actively forming stars, with visible nebulae like the Tarantula Nebula in the Large Cloud, a colossal star birth region. They orbit our Milky Way and are in the process of being gradually disrupted. A stream of gas, the Magellanic Stream, stretches behind them, torn off by our galaxy's gravity and the ram pressure of halo gas. In a few billion years, the Magellanic Clouds will likely merge into the Milky Way, adding their stars to our own. Besides these prominent examples, the Milky Way is encircled by many dwarf spheroidal galaxies, much smaller, fainter objects like Sagittarius, Draco, Ursa Minor, and Fornax. These tend to have little to no gas and consist mostly of ancient, faint stars. They often appear as just a sparse scattering of stars, detectable only with long exposures on large telescopes. The Sagittarius dwarf is actually in the process of being devoured by the Milky Way right now. It has been stretched into a long stream of stars, wrapping around our galaxy. Over time, its stars will assimilate into the Milky Way's halo. Each of these tiny galaxies is like a fossil record of the early universe. Many of them formed their stars more than 10 billion years ago and haven't done much since, preserving a snapshot of conditions shortly after galaxies began to form. Dwarf galaxies are incredibly valuable to astronomers as laboratories for dark matter and galaxy formation. They are the most dark matter-dominated galaxies known. In some ultra-faint dwarf galaxies, the few thousand stars move under the influence of a dark matter halo that outweighs them by hundreds or thousands of times. One extreme case is Segway 1, a diminutive Milky Way satellite so faint it has only a few hundred stars, yet they are held together by a blob of dark matter roughly 600,000 times the Sun's mass. That means Segway 1's mass is almost entirely dark matter, with a barely detectable glimmer of starlight. Measurements of star motions in tiny galaxies like Segway 1 or Triangulum 2 suggest that these systems might have up to 1,000 times more mass in dark matter than in stars. It's as if each faint dwarf is mostly a ball of dark matter with a sprinkling of stars. This makes them excellent testbeds for dark matter theories. How does dark matter cluster on small scales? Are the number of dwarf galaxies we see consistent with predictions from cosmological models? At first, there was a missing satellite problem. Computer simulations of cosmic structure predicted that a Milky Way-sized halo should have hundreds of smaller sub-halos orbiting it, potential dwarf galaxies. Yet for a long time we had observed only a few dozen around the Milky Way. Where were the rest? In the past 2 decades, however, new ultra-faint dwarf galaxies have been discovered in droves. The count of Milky Way satellites has climbed substantially, and we now suspect many more await detection, lurking in the shadows with extremely few stars. It seems that many dark matter sub-halos did form, but most of them failed to produce many stars, likely because the cosmic reionization heated and stripped gas from the smallest protogalaxies. Star formation in those puny halos was stifled, rendering them effectively dark. The ones we do see are the slightly bigger or luckier halos that manage to form stars despite these harsh conditions. The dwarfs that do shine provide crucial checks on our cosmological models. Their distribution around the Milky Way, their orbits, and their internal properties all carry information about how our galaxy were assembled. For instance, studies find that many of the Milky Way's dwarf satellites lie in a somewhat flattened arrangement, a feature still debated and potentially telling us something about past interactions or the filamentary nature of how they were acquired. The star formation histories of dwarfs also vary. Some, like the Magellanic Clouds, still form stars today. Others, like the dwarf spheroidals, formed most of their stars early and then stopped. Environment is a factor. Dwarfs near a big galaxy often lose their gas and thus cease making new stars, while isolated dwarfs farther away can retain gas longer. Dwarf galaxies are thought to be the building blocks of larger galaxies in the hierarchical model of cosmology. Over billions of years, small protogalaxies merged to build big ones. Essentially, today's large galaxies are the result of many past dwarf galaxy collisions and mergers. In our Milky Way's halo, astronomers identify remnants of several dwarf mergers beyond just Sagittarius. These show up as stellar streams or distinct groups of stars with common origins. The globular clusters orbiting our galaxy may include some that were originally brought in by dwarfs. In Andromeda, our nearest large neighbor, the halo is even more populated with substructures and streams, evidence of a rich history of consuming smaller companions. Dwarfs also affect their parent galaxies in subtle ways. A satellite can tug on the primary galaxy via gravity. For example, the Large Magellanic Cloud is massive enough that it's pulling on our galaxy, causing both to move toward their common center of mass. Interactions between a dwarf and a large galaxy can create disturbances. The Milky Way's disk has ripples and warps, possibly induced by past encounters with satellites. And when a dwarf with fresh gas orbits a big galaxy, it can funnel gas into the big galaxy's halo, which may later rain down and fuel future star formation in the main galaxy. Thus, dwarfs can be providers of material, not just victims. They might extend the star, forming life of a big galaxy by donating gas during their infall. Because of their small size, dwarf galaxies also highlight the thresholds and extremes of galaxy formation. They exist in regimes where a single burst of star formation can exhaust their supply or blow out what's left. Some dwarfs show evidence of one ancient burst and then long quiescence. Others, in isolation, might have sporadic bursts separated by many millions of years as gas slowly pools in again. Some tiny galaxies may have been completely stunted by the ionizing glare of the first stars and quasars during reionization, never forming many stars at all. They remind us that not all galaxies are the continuously rotating, long-lived star factories like the Milky Way. Some are stop and go, some are one and done, and everything in between. In summary, dwarf galaxies may be small, but they are crucial pieces of the cosmic puzzle. They were the first galaxies to form, the building blocks that merged into larger ones. They are the most common galaxies by number. They are reservoirs of dark matter, offering evidence for its behavior on small scales. And as satellites, they are constantly interacting with larger galaxies, being pulled apart, contributing gas and stars, and generally complicating the life of their big hosts. In their diminutive form, dwarfs carry outsized importance for understanding gravity, dark matter, and the history of galaxy assembly. Having explored these miniature galaxies, we now widen our perspective to the enormous patterns that galaxies themselves form on the grandest scales. Just as stars gather into galaxies, galaxies congregate into clusters, superclusters, and filaments in a vast cosmic web. It's time to venture into the large-scale structure of the universe, the architecture of galaxies on cosmic scales. The cosmic web, clusters, superclusters, and filaments. Galaxies, including the Milky Way, are not scattered randomly through space. They often gather in larger structures bound by gravity. On the first rung of this cosmic ladder are galaxy groups. A galaxy group generally holds a few dozen or fewer galaxies. The Milky Way and Andromeda, along with the dozens of dwarf galaxies orbiting them, form the local group, a collection of more than 50 galaxies spanning about 10 million light-years. Our local group is a typical small cluster. It has two dominant spirals, a third spiral, and many dwarfs. The galaxies in the local group orbit their common center of gravity and are bound together. Step up in scale, and we find galaxy clusters. These are much larger assemblies, containing anywhere from hundreds to thousands of galaxies, all bound in a single gravitational swarm. Galaxy clusters are among the most massive coherent structures in the universe. A good example is the Virgo cluster, the nearest sizable cluster, roughly 50 million light-years away in the direction of the constellation Virgo. It holds over 1,000 galaxies in a volume a few million light-years across. The cluster's core is crowded with elliptical galaxies, including a giant central galaxy sitting at the center, feasting on smaller galaxies that venture too close. Clusters like Virgo are permeated by a hot X-ray, emitting gas that fills the space between galaxies. This intracluster gas actually outweighs all the stars in the cluster, and dark matter outweighs both. Clusters are dark matter, dominated just like galaxies, but on a larger scale. The galaxies in a cluster move at hundreds or even over 1,000 kilometers per second, ricocheting through the cluster's deep gravitational well. Clusters themselves aren't isolated. They often lie in larger complexes called superclusters. A supercluster is essentially a cluster of clusters, an extended grouping of galaxies, groups, and clusters spanning perhaps a few 100 million light-years. Our local group, for instance, is on the outskirts of the Virgo supercluster, which contains the Virgo cluster and dozens of other groups and clusters in our corner of the universe. In recent years, astronomers have realized that what we used to call the Virgo supercluster is part of an even larger complex named Laniakea, a Hawaiian word meaning immense heaven. The Laniakea supercluster, as mapped by the flow of galaxies, includes the Virgo cluster, the Hydra, Centaurus supercluster, and other clusters, all linked by gravity. It stretches over 500 million light-years and contains the mass of perhaps 100,000 galaxies. At the center of Laniakea is a gravitational focal point dubbed the Great Attractor, a region of space causing a peculiar motion of our local group and others toward it. This Great Attractor's pull is part of the evidence of Laniakea's extent. Connecting these clusters and superclusters are the filaments, long strings of galaxies and galaxy clusters, tens to hundreds of millions of light-years long, but relatively thin. Between the filaments lie voids, enormous regions with very few galaxies, sometimes tens of millions of light-years across where only a handful of galaxies dwell. One famous void, the Boötes void, is about 330 million light-years in diameter and contains very little. It's been whimsically described as a spherical space with nothing in it, though in reality there are a few galaxies scattered within. The contrast between filaments and voids gives the universe a kind of foamy texture. Some filaments can join together into sheet, like structures or walls. For example, the Sloan Great Wall, identified in large galaxy surveys, is a massive thread of galaxies and clusters, about 1.5 billion light years long, among the largest structures ever observed. The cosmic web's appearance is often compared to a sponge or foamy bubbles, concentrations of matter surrounding vast empty voids, or even to the brain's neural networks on a cosmic scale. This arrangement, clusters, superclusters, filaments, and voids, is what we call the cosmic web. It formed from the same primordial fluctuations we discussed earlier, amplified by gravity over cosmic time. Dark matter played the key role. It clumped into filaments early, and ordinary matter followed, flowing into those gravitational channels to form galaxies. The result is that on the grandest scales, matter in the universe is arranged in twisting, thread-like structures with immense voids in between. When we run large computer simulations of the universe, starting from the initial conditions of the Big Bang and letting gravity draw matter together, a filamentary pattern naturally emerges. The simulation's output, when compared to maps of real galaxies from surveys like the Sloan Digital Sky Survey, is strikingly similar. It's one of the triumphs of modern cosmology. The cosmic web we observe is exactly what our theories predict given dark matter and the expanding universe. To give a sense of scale, an individual galaxy might be 100,000 light years across, a cluster 10 million, a supercluster 200 million, the distance between major superclusters on the order of 1 billion light years. The observable universe is about 93 billion light years in diameter. On those largest scales, the cosmic web starts to blend into homogeneity. An extremely large cube of the universe would contain a statistically even mix of galaxies and voids. But up to those enormous scales, the web is evident. It's breathtaking to realize that the Milky Way, with all its hundreds of billions of stars, is but a single point on the vast cosmic web, a node in a structure so immense it defies full comprehension. In a thought experiment, imagine pulling back your vantage point. Zoom out from our solar system, past the Milky Way's disk, until our whole galaxy is just a glowing spiral among others. Zoom further, and the Milky Way and its neighbors blend into the local group, a small cluster of galaxies. Pull back more, the local group becomes just one clump in the Virgo cluster. Further still, the Virgo cluster and adjacent groups merge into the Laniakea supercluster, a great flowing concentration of matter. Finally, as you zoom to a view hundreds of millions of light years across, the superclusters themselves line up as filaments, the cosmic web revealed in its entirety, galaxies like grains of dust, tracing the grand design of gravity. This mental journey underscores how nested our existence is within ever grander systems. We live within this web. Our Milky Way, Andromeda, and neighbors float together in the local group, which is being gently pulled as part of the Virgo Laniakea supercluster along a filament towards the Virgo cluster. In far, far future billions of years, that journey might bring our remnants into Virgo's embrace. When we peer out at the night sky, the stars we see with the naked eye all belong to our own galaxy, but the faint smudges we see through telescopes are all part of this grand structure. For instance, the Coma cluster of galaxies appears as a dim patch in the constellation Coma Berenices, but it is the heart of a rich filament connected to other clusters. The Shapley supercluster, one of the most massive supercluster concentrations known, is another knot in the web observable in southern skies. The cosmic web is not just a backdrop, it influences how galaxies evolve. Galaxies in clusters are different from those alone in the field. They tend to be redder and gas poor, partly due to interactions and the hot cluster environment stripping their gas. Galaxies riding along thin filaments can funnel towards clusters, often getting processed by smaller group environments before entering a cluster. Thus, a galaxy's larger scale environment plays a role in its story, illustrating the adage, location, 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 on a cosmic scale. It's remarkable to think that barely 100 years have passed since we even confirmed galaxies outside the Milky Way. Now, with our arsenal of observations and simulations, we have mapped the architecture of the universe on the largest scales. We have, in essence, discovered the blueprint of creation's vast cosmic web. Having charted out this grand design, we turn to some of the most puzzling denizens of this landscape, galaxies that challenge our definitions, those that are extremely diffuse or even seemingly made mostly of dark matter with hardly any stars. These ultra, diffuse and dark galaxies push the boundaries of what a galaxy can be, and exploring them will deepen our insight into the unseen components of the universe. Ghostly galaxies, ultra, diffuse and dark galaxies. Not all galaxies are the bright, well-defined islands of stars we might imagine. In recent years, astronomers have discovered a class of galaxies so faint and spread out that they've been called ultra, diffuse galaxies, ghostly apparitions barely visible against the night sky. These galaxies can be as large in extent as the Milky Way, yet have only a tiny fraction of the stars. Picture a galaxy with the diameter of a giant spiral, but the total luminosity of a dwarf galaxy, effectively a huge puff of stars so sparse that if you lived inside it, you might not realize you were in a galaxy at all, because the stars would be so few and far between. One example that made headlines is Dragonfly 44, a faint galaxy in the Coma cluster. When first studied, Dragonfly 44 appeared to have about the mass of the Milky Way, but only about 1% of the number of stars, implying it was 99% dark matter by mass. It was dubbed a failed galaxy, or a dark matter galaxy, as if it started forming like a normal large galaxy, but somehow failed to produce many stars. Dragonfly 44 also sports an unusually rich system of globular clusters for its luminosity, supporting the idea that it once had the potential to be a big, star-filled galaxy, but didn't follow through. This and other UDGs beg the question, how do you get a galaxy that big with so few stars? There are several ideas. One is that these UDGs formed in high-spin halos. The gas was spread out over a larger area and thus never condensed into the dense concentrations needed for prolific star formation, resulting in an oversized but dim galaxy. Another idea is tidal heating. Perhaps they were once normal galaxies that got puffed up by gravitational tides in a cluster environment, stretching them out and thinning their star distribution. Some might be failed giant galaxies. Their dark matter halo and initial gas were like that of a large galaxy, but something prevented normal star formation. What remained is a dim shadow of a galaxy, mostly dark matter, holding a thin sprinkling of stars. On the other extreme of the spectrum are reports of galaxies that seem to have very little dark matter at all. In 2018, astronomers announced the discovery of a galaxy named NGC 1052, DF2, that defied expectations. This diffuse galaxy, about the size of a dwarf, appeared to have so few stars that one would expect it to be dominated by dark matter, yet the velocities of those stars were so low that they implied the galaxy's mass was nearly all accounted for by the visible stars. In other words, it seemed to lack the unseen mass that every other galaxy its size needed. A year later, a second galaxy in the same group, DF4, was found with similarly anomalous properties. These no-dark matter galaxies caused a flurry of both excitement and skepticism. If true, they would be the first galaxies discovered that contradict the rule that galaxies form within dark matter halos. Could it be that dark matter can be stripped entirely from a galaxy, leaving behind a wraith of stars? Or might there be an alternative explanation? One possibility is that these galaxies did form in normal dark matter halos, but later experienced a gravitational interaction that sheared away most of their dark matter. For example, if DF2 and DF4 passed very close to a much larger galaxy, the tidal forces could have pulled out a large fraction of their dark matter and outer stars, leaving behind an inner core of stars with little surrounding halo. Another clue, DF2 and DF4 both have unusual populations of globular clusters, fewer in number, but unusually luminous for the galaxy's size. This might hint that something about their formation was atypical. Some later studies argued the distance to these galaxies might have been overestimated initially. If they are a bit closer than first thought, then they have fewer stars, and the original no dark matter conclusion may soften. The jury is still out, but most scientists suspect these galaxies aren't truly dark, matter-free, but rather odd products of interactions. Important nonetheless, because they show how far interactions can go in reshaping a galaxy. When we say dark galaxies, we could also mean the purely hypothetical objects made almost entirely of dark matter, with virtually no stars at all. Our cosmological models predict that there should be many small dark matter halos that failed to form stars. These would be completely invisible to us, except through gravitational effects. Detecting one directly is extremely challenging. How do you see an object that emits no light? One strategy is via 21 pound-centimeter radio surveys of hydrogen gas. Astronomers have searched for isolated clouds of hydrogen, with motions indicating they are held together by some mass, yet with no visible stars, essentially a dark galaxy candidate. A few candidates have been reported. One famous one, discovered in the Virgo cluster, was a large cloud of hydrogen that some thought might be a dark galaxy. However, skepticism remains, as it's hard to distinguish a truly dark galaxy from tidal debris. So far, no incontrovertible 100% dark galaxy has been confirmed. But the hunt itself is telling. If we found even one, it would confirm that starless galaxies can exist and would be a direct piece of evidence for the prevalence of dark matter halos without baryons. What do these ghostly galaxies tell us? For one, they underscore the complex interplay of matter in galaxies. We have galaxies like ultra, diffuse ones that are heavily dominated by dark matter, and perhaps others that are so dominated by normal matter that they barely show dark matter's presence. This diversity challenges our understanding of galaxy formation. Our theories have to accommodate both ends of this spectrum. They also serve as natural experiments. For example, a galaxy lacking dark matter would be a huge test for alternative theories of gravity, which predict you can't have one without the other. Conversely, galaxies with extreme dark matter dominance test our models of star formation efficiency. Why did they form so few stars relative to their dark mass? Ultra, diffuse galaxies also likely hint at the role of environment. The fact that many UDGs are found in clusters suggests that environment, e.g. interactions with other galaxies or the cluster's tidal field, might be responsible for their puffed-up nature. They might be the blown-out remains of formerly normal galaxies that got their gas removed early and their structures distended. In less dense environments, such fragile, puffy galaxies might not survive. The cluster both creates them and, ironically, helps preserve them by confining them in its gravitational embrace. As we continue exploring these extreme galaxies, we sharpen our understanding of the thresholds of galaxy formation. We learn what it takes for a dark matter halo to actually light up with stars, and what circumstances can prevent it. We see how galaxies can be stripped to the bone by interactions, and how nature can produce objects that challenge the very definition of a galaxy. After all, a galaxy has traditionally been defined as a gravitationally bound collection of stars. But what do we call a gravitationally bound collection of mostly dark matter and almost no stars? Or conversely, a tenuous collection of stars that seems to have shed its dark matter? These edge cases blur the lines, forcing us to refine our definitions. The mysteries of ultra, diffuse and dark galaxies remind us that there is still much to learn about the invisible scaffolding of the cosmos. With new telescopes and surveys, we are now better equipped to find more of these phantom galaxies and unravel their stories. Each such discovery is like finding an unexpected creature in the cosmic wilderness, challenging what we thought galaxies could or couldn't be. After exploring the extremes of galactic forms, from the magnificent to the barely there, we return now to the grand perspective of the universe. We've spoken of countless galaxies, but how many can we actually see? How far does our vision reach? Next, we'll discuss the observable universe, how deep our telescopes peer into the cosmic past, how many galaxies likely populate our universe, and what lies at the edge of our sight. The observable universe, counting galaxies and reaching back in time. Our journey through the cosmos has taken us from our own Milky Way to the farthest reaches of galactic existence. One naturally wonders, how many galaxies are there? And how far can we see into the depths of space and time? The truth is both humbling and exhilarating. When the Hubble Space Telescope pointed its lens at what seemed to be an empty patch of sky in 1995 for 10 days, the resulting image, the Hubble Deep Field, revealed thousands of galaxies of all shapes and colors packed into that tiny speck of sky. This was followed by the Hubble Ultra Deep Field in 2004, an even longer exposure that unveiled nearly 10,000 galaxies in an area of the sky only a fraction of the moon's apparent size. Every swirl, blob, and smear in those deep images was an entire galaxy, some as they were over 13 billion years ago. Extrapolating these results to the whole sky suggested that the observable universe contains on the order of hundreds of billions of galaxies. For a long time, a common estimate was around 200 billion galaxies in the observable universe. But even that might be an underestimate. In 2016, using data from new surveys and some clever modeling, astronomers proposed that there could be as many as 1-2 trillion galaxies in the observable universe. Many of those would be very small, faint galaxies, the kind that current telescopes can't easily see, especially those that existed in the early epochs of the universe. It's sobering to realize that every time you look at a clear night sky, the few thousand stars you see belong to our Milky Way. Yet overhead, invisible to our eyes, are billions upon billions of other galaxies, each with its own stars, planets, and perhaps life, scattered across the universe. The phrase observable universe is key. It refers to the portion of the universe from which light has had time to reach us since the Big Bang. Because the universe is about 13.8 billion years old, and space has been expanding, the current radius of the observable universe is about 46 billion light years. That encompasses an immense volume. Think of a sphere centered on Earth that includes all galaxies, whose light has traveled 13.8 billion years or less to get here. Galaxies beyond that horizon are simply too far for their light to have ever reached Earth in the age of the universe. They may exist, but we cannot see them, and they cannot see us. How far have we seen? With the Hubble Space Telescope, we detected galaxies at around 13.3 billion years look back time. One example was a galaxy nicknamed GN-Z11, observed in Hubble's deep surveys at a redshift of about 11. That was a record for some years. Now, thanks to the James Webb Space Telescope, we've pushed the frontier even closer to the dawn of galaxies. In 2022-2023, JWST identified galaxies with tentative redshifts of 13, 14, even up to around 16, if confirmed. Those correspond to times just 250-300 million years after the Big Bang. We are likely seeing the flicker of some of the first generations of galaxies that formed in the universe. These farthest galaxies are tiny and primordial, looking often irregular agglomerations of stars, blazing with the light of massive newborn stars, but relatively low in mass. They lack the heavier elements that subsequent generations of stars would build up. Observing them is like peering back in time to watch the universe's infancy, the cosmic dawn, when the first galaxies and quasars burst into light and began reionizing the fog of hydrogen that filled space after the Big Bang. Each new leap in telescope power effectively extends our time machine further. JWST is now letting us study in detail the era when the very first galaxies took shape. So, how many of those galaxies can we actually see? In practice, even with our best telescopes, we cannot see all the hundreds of billions of galaxies out there. Many are too faint or too redshifted. But we can see an astonishing variety. From the grand spirals a few million light years away, to ancient red ellipticals in distant clusters billions of light years away, to tiny blue specks that are infant galaxies in the early universe. As telescopes improve, our observable catalogue of galaxies grows. The upcoming Vera C. Rubin Observatory will map billions of galaxies across the sky, though mostly relatively nearer ones. Space telescopes like JWST and the planned Nancy Grace Roman Space Telescope will focus on finding and analyzing the faint distant ones. What does this reveal about the universe's timeline? By surveying galaxies at different distances, we can trace the evolution of galaxies over cosmic time. We see that in the early universe, galaxies were generally smaller, more irregular, and forming stars at a furious rate. Many were clumping together and merging. As time went on, small galaxies combined into larger ones, star formation peaked, and then gradually declined. Galaxies in the more recent universe often appear larger, more mature, with well-defined structures like spiral disks or big diffuse ellipticals, and many have slowed their star formation. By looking as far back as JWST allows, we're trying to witness the moment when the very first stars and galaxies ended the cosmic dark ages. We also glean the universe's timeline from the most distant light of all, the cosmic microwave background. This is not a galaxy, but the faint remnant glow of the Big Bang itself, released about 380,000 years after the Big Bang, when the hot plasma cooled enough for atoms to form and light to travel freely. The CMB comes to us from every direction, a nearly uniform background with tiny fluctuations that encode the seeds of future galaxies and clusters. It represents the absolute limit of what we can see via electromagnetic radiation. Beyond that, the universe was opaque. It's like a foggy wall at the edge of our vision. We cannot see through the CMB with light. It's the backdrop of the observable universe. Thus, our observations currently span from the present day all the way back to those first few 100 million years, when the earliest galaxies and black holes were turning on, and finally to the CMB wall at 13.8 billion years ago. Each big telescope and survey has effectively peeled back another layer of the universe's history. Our picture of the cosmos's timeline has grown rich. We have seen the universe as a baby, as a rambunctious toddler, as a vigorous youth, and in its middle age. As for how many galaxies exist in total, the number is truly mind-boggling and might ultimately be unanswerable if the universe is infinite. But in the observable volume we inhabit, current best estimates suggest on the order of 1 trillion galaxies. It's a number so large it loses meaning. Suffice it to say, there are more galaxies in the observable universe than there are stars in any individual galaxy. Looking up at a dark sky, one might feel that the universe is mostly empty darkness sprinkled with stars. But thanks to our instruments, we know the opposite is true. The darkness is filled with the light of galaxies, stretching to the edge of what is knowable. Standing here, on a small planet within the Milky Way, we have managed to gauge the universe's extent and populate it with galaxies by the billions. This achievement of human curiosity sets the stage for our final reflections on what it means to live in a universe so vast and full of galaxies, to be made of the stuff of stars, and to contemplate it all from our tiny corner of the cosmic ocean. Eyes on the cosmos, telescopes that revolutionized our view. Our understanding of galaxies has expanded hand in hand with the advancement of our telescopes, our eyes on the universe. Even before the space age, giant ground-based telescopes pushed our galactic knowledge. The 100-inch Hooker telescope on Mount Wilson in the 1920s allowed Edwin Hubble to measure galaxies' distances and the expansion of the universe. The 200-inch Hale telescope at Palomar was the world's largest for decades. It revealed exquisite details in galaxies and allowed astronomers in 1963 to identify the first quasar, realizing it was an unbelievably distant powerhouse. Each leap in technology has brought a leap in knowledge. In particular, a few key instruments and missions have transformed our view of galaxies in ways earlier astronomers could only dream of. The Hubble Space Telescope, launched in 1990, has been often called one of the most productive scientific instruments ever built. Above the blurring effect of Earth's atmosphere, Hubble has provided crystal, clear images of galaxies near and far. It showed us spiral galaxies in unprecedented detail, glittering arms and delicate dust lanes, and peered into the cores of ellipticals to find evidence of central black holes. Hubble's most famous contribution might be its deep field observations. By staring at empty patches of sky for days, HST captured the Hubble Deep Field and Ultra Deep Field, revealing a rich backdrop of galaxies stretching to the horizon of the universe. These images fundamentally changed our perception. Every tiny patch of sky, if you look long enough, is teeming with galaxies. Hubble also provided distance measurements via Cepheid variables and supernovae that helped nail down the scale of the universe and the rate of its expansion. Its crisp images of galaxy collisions, gravitational lensing arcs, and proto-galactic fragments have filled textbooks and our collective imagination. If Hubble opened a clear window in visible light, the James Webb Space Telescope, launched at the end of 2021, has opened a new window into the infrared universe. Galaxies emit light across the spectrum, and by looking in the infrared JWST, can see through dust clouds that obscure stellar nurseries and detect the faint glow of extremely distant galaxies whose light has been stretched into the infrared by the expanding universe. In its first years of operation, JWST has already identified some of the earliest galaxies ever observed, spotted rich organic chemistry in galaxy gas clouds, and produced stunningly detailed images of galaxies like never before. JWST's ultra-sensitive infrared vision is giving us a direct look at the cosmic dawn, complementing Hubble's view of the later universe. Together, Hubble and Webb act like time machines, Hubble mapping the middle epochs and Webb pushing toward the beginning. Beyond these two famous space telescopes, there have been and are many other missions that significantly advanced galactic astronomy. Radio telescopes. In the mid-20th century, radio dishes like those at Jodrell Bank and later the Very Large Array in New Mexico started mapping radio emission from galaxies. They discovered jets and lobes emanating from active galactic nuclei. Radio surveys found quasars before we knew what they were. Bright radio sources with star-like optical counterparts that turned out to be distant AGNs. Today, radio telescopes like ALMA can detect the cold molecular gas in galaxies billions of light years away, revealing where future stars will form and how galaxies acquire fuel. They also measure the rotation of outer gas in galaxies to chart out dark matter distributions. Interferometric radio images of colliding galaxy clusters have even detected the shock waves of cluster mergers and the halo radio glow from cosmic ray electrons in cluster-scale magnetic fields. X-ray observatories, space-based. X-ray telescopes, such as Chandra and XMM, Newton, have shown us the high-energy side of galaxies. They map the X-ray glow of hot gas in galaxy clusters, providing direct measurements of cluster masses. Chandra's sharp vision revealed how clusters collide. X-ray images of galaxies show the halo of hot plasma that many galaxies, especially ellipticals, sit in, and pinpoint the light from accreting black holes at galactic centers or ultraluminous X-ray binaries sprinkled throughout galaxies. X-ray surveys also discovered mysterious diffuse X-ray backgrounds, and contributed to the discovery of intergalactic filaments of warm, hot gas connecting clusters. Infrared and UV surveys. Before JWST, we had Spitzer, which, though smaller, detected countless dusty stars, forming galaxies, and helped uncover ultra-luminous infrared galaxies. Spitzer observed high, redshift galaxies in infrared 2, bridging some of the gap until JWST. In the ultraviolet, the Galactic Space Telescope mapped UV emission across the sky, highlighting where in galaxies young massive stars are concentrated. Galac's pictures of spirals showed hazy UV halos of star formation and star streams, and captured starburst activity in dwarfs and interacting galaxies. Ground-based surveys and upcoming telescopes. The Sloan Digital Sky Survey, starting in the 2000s, used a dedicated 2.5-meter telescope to perform an immense imaging and spectroscopic survey of galaxies. SDSS gave us a 3D map of over 1 million galaxies, which led to the discovery of large-scale structures, like the cosmic web filaments, and refined our understanding of galaxy demographics. The forthcoming Vera C. Rubin Observatory in Chile will take this further, imaging the entire visible sky to great depth repeatedly and capturing billions of galaxies and their changes over time. The Nancy Grace Roman Space Telescope will conduct wide field surveys at near-infrared, providing a Hubble-like clarity, but on areas of sky hundreds of times larger, ideal for finding distant galaxies and mapping dark matter via weak gravitational lensing. And on the ground, the new extremely large telescopes will, later this decade, give astronomers unprecedented power to study faint galaxies and directly image features in galaxies tens of millions of light years away that currently appear as mere smudges. They'll also dissect the light of very distant galaxies into spectra to determine their compositions and internal motions in detail, complementing Webb's work with brute force light, gathering, and sharp resolution. Each of these tools, whether in space or on the ground, has peeled back a layer of the cosmic onion, bringing galaxies into better focus. Our toolkit now spans the full electromagnetic spectrum: radio, microwave, infrared, optical, ultraviolet, X-rays, and gamma rays. By combining all these views, we get a holistic picture of galaxies that was impossible a century ago. It's remarkable to think that barely a lifetime ago, we didn't even know other galaxies existed. Now, with our Hubbles and Webbs and myriad other instruments, we routinely catalogue galaxies billions of light, years distant, capture images of their shapes, break their light into spectra to gauge their compositions and star formation rates, and even watch as they collide or as their cores light up as quasars. Missions like Hubble and Webb stand as milestones in this ongoing journey, each bringing the universe's galaxies closer to us. As we consider these powerful tools and the discoveries they have enabled, we prepare to leave the domain of scientific observation and enter a more introspective realm. With the data gathered by these instruments, we can now reflect on what it means to live inside a galaxy, to be made of stars, and to find our place in cosmic time. In the final section, we'll step back from the technical and immerse ourselves in the philosophical and existential implications of knowing that we are part of a universe filled with galaxies. Reflections. Our place among the galaxies. On a warm, clear night, if you find yourself far from city lights, you can see the Milky Way arching overhead, a milky band of light splashed across the sky. That soft glow is the combined shine of billions of distant stars in our home galaxy, seen from within. We live inside a galaxy embedded about 26,000 light years from the Milky Way's center, orbiting with our sun and planets among the spiral arms. For most of human history, we didn't know that we were inside a galaxy, or even what a galaxy was. Now, in the light of all we've learned, think about what that means. It means that when you gaze up at the Milky Way, you are seeing the structure of our galaxy from the inside, the disk of stars and nebulae in which our Sun is just one modest member. It means that our Sun is one of perhaps 400 billion stars in the Milky Way, and our Milky Way is one of perhaps 1 trillion galaxies in the observable universe. Our Earth is a tiny world circling a garden, variety star, in the outskirts of one galaxy, among uncountable others. This realization can make one feel incredibly small. The scales are almost too vast to hold in the mind. The distance to even the nearest major galaxy, Andromeda, is 2.5 million light years, so far that the light hitting your eye tonight from Andromeda left that galaxy when early human ancestors were just beginning to make stone tools. And yet, consider the flip side. Though we are tiny, we are also a part of this grand universe. We are made of it. The iron in your blood, the calcium in your bones, the oxygen you breathe, those atoms were forged long ago in stars, likely in the Milky Way, during stellar alchemy and violent supernova explosions. We are made of stuff, the products of galactic recycling. Over the history of our galaxy, generations of stars lived and died, each enriching the cosmic clouds with heavier elements, which eventually found their way into the gas that formed our Sun, our planet, and ultimately us. In a very literal sense, the galaxy is in our bodies. We are the universe, in a small way, contemplating itself. As one philosopher, scientist mused, we are a way for the universe to know itself. Atoms with curiosity, as someone once said. From our vantage point on Earth, we've managed to decipher the Milky Way's structure, learn the history of galaxies, and even map the large-scale cosmic web. Feats of understanding accomplished by a clever species of primate using telescopes and mathematics. It's astonishing. The universe became aware of itself through us. We, tiny and fragile, can mentally span billions of light, years and billions of years, reconstructing events and structures we will never physically touch. When we look at a picture of a distant galaxy, we're seeing a piece of the universe's autobiography, a chapter from a time and place utterly remote, yet connected to us through the simple act of a photon of light traveling across space and landing in a telescope mirror. To live inside a galaxy is to be both extremely insignificant and extremely special. Insignificant because the galaxy does not notice us. The Milky Way would be essentially unchanged if our solar system vanished tomorrow. We occupy no central role. The universe is not arranged with us in mind. But special because despite that, we have the unique gift of consciousness to appreciate the cosmos. The stars in the Milky Way burn on obliviously, yet here on a rocky planet around one star, the atoms assembled into beings that can admire the beauty of a spiral galaxy, that can feel awe at the sight of the Milky Way's shimmering band, that can wonder about the possibility of other minds in those other galaxies doing the same. We have, in a sense, imbued the galaxy with meaning simply by being here to observe it. Galactic timescales stretch far beyond human lifetimes. Our solar system orbits the galaxy every 230 million years, making one galactic year. A human life is a mere instant by that clock. In fact, when dinosaurs roamed the Earth, it was roughly one galactic year ago. In one sense, that might make our lives feel vanishingly short, but it also means that life on Earth is tied into the dynamic life of galaxies. Civilizations might rise and fall while galaxies perform their slow gravitational dance. Perhaps in some distant future, beings will witness the night sky dramatically change as the Milky Way merges with Andromeda. None of us will see that, but knowing it will happen connects us to the far future and to the long narrative of our galaxy. When confronting these immensities, it's natural to ask, what do galaxies mean for us? They can make our everyday concerns feel small, the petty squabbles, the borders we draw on our tiny planet. Viewed against the cosmic backdrop, such things seem trivial. Many astronauts, after seeing Earth from space against the void, report a profound overview effect, a shift in perspective, recognizing the unity and fragility of life on our pale blue dot. A similar effect comes from the cosmic perspective, recognizing that all humanity shares one tiny home galaxy, that we have far more in common with each other than any difference, and that our true tribe is as large as the Earth, perhaps even as large as the Milky Way. We are all voyagers together through the galaxy. There is also a deep comfort and inspiration in this perspective. The atoms that make us have endured across billions of years and multiple galaxies' journeys. They will persist long after we are gone, possibly incorporated into new living beings or new worlds when our sun's time is over. We are part of something continuous and far bigger than ourselves. The light we make, radio waves carrying our broadcasts, for instance, is even now leaving the Milky Way and traveling into intergalactic space. In that sense, a piece of us will touch other galaxies, albeit faintly. Knowing about galaxies also invites a profound humility. We inhabit a universe where the dramatic and the sublime are commonplace. Galaxies crash together, black holes light up as quasars, stars are born and die in colorful nebulae. Entire clusters of galaxies dance in gravity's grip. Against such a backdrop, the significance we assign to our own achievements or struggles finds a healthy perspective. But rather than make us feel despair at our smallness, this awareness can instill a sense of gratitude and wonder. Out of all the possibilities, we have the privilege to witness and understand a slice of the universe's story. Finally, consider that for most of history, the galaxies were unknown to us. Only in the last century have we recognized what the spiral nebulae truly are. In that short time, essentially a couple of human lifetimes, we've gone from not even knowing other galaxies exist to mapping the cosmos and decoding the light from the dawn of time. This rapid progress shows something powerful. Our desire to learn is as expansive as the universe itself. We are a curious, bold species, unafraid to ask big questions. What is that hazy band in the sky? What are those faint smudges in the telescope? How did we come to be? And remarkably, we've been able to answer many of them. As we conclude the story of galaxies, we find that it is deeply intertwined with our own story. Galaxies are not just distant objects. In a very real way, they are our extended homes. The Milky Way gave birth to the Sun and Earth. Galaxies provided the raw materials for life and the stage for every cosmic event that led to our existence. When we marvel at the galaxies, we are in a sense marveling at our origins. And we are fortunate to live at a time when we can see them. Eons from now, the expansion of the universe will carry many galaxies beyond our observable reach, potentially leaving future civilizations more isolated. We, however, inhabit a cosmic epoch rich with galaxies to observe and learn from. So, the next time you find yourself under a truly dark sky, allow yourself a moment of communion with the Milky Way. Think of the myriad stars you see and know that you are connected to them, that you are made of their fire, that your existence is tied to their past. Think of the countless galaxies beyond, each with its own wonders and perhaps its own watchers. Feel the swell of awe that comes from realizing you are part of a cosmos so vast and magnificent. In that feeling lies something profoundly human and profoundly beautiful, a sense of belonging to the universe itself. In the beginning, there is nothing but darkness. For ages untold, after the birth of the universe, there is no light, only a silent void and the cooling embers of the Big Bang. Imagine this primordial darkness. No stars, no galaxies, just an endless night stretching millions of years. Yet in that darkness, something is stirring. Gravity is gently pulling together clouds of pristine hydrogen gas, gathering and squeezing them in invisible hands. Deep in one such cloud, pressure mounts, atoms collide, and heat rises. There is a tremor in the void, a hint of radiance forming, still hidden. Then, suddenly, light. A blinding spark erupts where there was none before. In an instant, the first star ignites. The cosmic dark ages end in a flood of starlight. It is the universe's first sunrise. A lone star has begun to shine, pouring out photons into the black abyss. Soon, another star kindles, and another. The newborn cosmos sprinkles itself with tiny islands of light. The darkness of creation is pushed back by these early fires, and the cosmic dawn has arrived. What was once cold and black is now dappled with the warm glow of starlight. Eons later, on a small young planet orbiting a later generation of those stars, there comes another first sunrise. Picture Earth over 4 billion years ago, a barren world of rock and boiling seas under a choking sky. The air is thick with volcanic fumes and the dust of creation. As the planet cools, its skies begin to clear. One morning, the clouds part to reveal a brilliant glow on the horizon. Dawn breaks over Earth's primordial landscape. For the first time, sunlight bathes the craters and steaming oceans of our world. The infant sun climbs over the horizon, and day begins on Earth. The planet's surface, once lit only by lava and lightning, now knows the gentle illumination of a star. That first sunrise would have been an alien scene. No life to witness it. Only chemistry and stone. Yet it was a harbinger. From that day onward, every living creature on Earth would be born to a world warmed and lit by a star in the sky. Our sun had arrived in our heavens, and nothing would ever be the same. Ancient reverence. From the moment humans first opened their eyes under its golden light, we have felt the sun's power. Long before science, we knew in our bones that our lives depended on that glowing orb. Every dawn brought light and warmth. Every dusk brought its absence. In the sun's daily rising and setting, ancient peoples saw the dance of gods and the rhythm of existence. So across cultures and centuries, mythologies blossomed around the sun. Our star became our deity, our timekeeper, our source of life in story and song. In ancient Egypt, the sun was Ra, the falcon-headed god who sailed across the sky by day in a great barge and descended into the underworld at night. Each sunrise was Ra's triumphant return after vanquishing the darkness. Egyptians tilted their faces to the dawn and felt the touch of a divine father. Far to the east, Vedic hymns of India praised Surya, riding a chariot led by 7 shining horses, bringing light, dispelling evil, and watching over all creatures. In the clear air of the Andes, the Inca honored Inti, the radiant patron of empire, believed to be an ancestor of their kings. Temples and treasures were devoted to Inti's glory. The sun's daily journey inspired vivid imagination. The Greeks envisioned Helios, a titan crowned with rays, steering a fiery chariot drawn by stallions across the sky from east to west. Each evening, Helios would descend at the horizon and embark on a nightly voyage in a golden cup back to the east, so he might rise again. His Roman counterpart Sol, and later Sol Invictus, the unconquered sun, symbolized continuity and victory over darkness. In Japan, the sun was personified as Amaterasu, the great goddess of light. When she hid herself in a cave out of grief, the world was plunged into darkness until the other gods lured her out, restoring light and hope. Every culture found its own language for the sun's gift. The Norse spoke of the goddess Sol, forever chased by a giant wolf across the sky. At the end of days, they feared the wolf would catch her, and darkness would consume the world. The Aztecs offered beating hearts to Tonatiuh, the sun of the 5th age, believing only constant sacrifice could fuel the sun's strength to rise each day. In Mesopotamia, mighty Shamash not only lit the day, but also saw all, becoming a god of justice, shining his light on the truth. The Chinese told of 10 suns that once scorched the world until only one was left to give gentle light. The sun has been a wheel of fire
an eye in the sky, a divine torch carried by various hands in human imagination. We built monuments to chase the sun's movements. On Salisbury Plain, Stonehenge's stones were carefully aligned with the solstice sunrise, so the first ray on midsummer's morning would pierce straight to the heart of the circle. In temples and pyramids across the world, from Abu Simbel in Egypt to Angkor Wat in Cambodia, architects aligned doorways with the sun, capturing its light on sacred altars on specific days of the year. To ancient peoples, these moments when the sun's light perfectly struck their creations felt like communion with the heavens. The sun told them when to sow and when to reap, marking seasons with its ever-changing arc in the sky. A stable sun meant abundance. An eclipse or an unexplained dimming could instill terror that the gods were angry or the end was nigh. In prayer, in ritual, in art, humanity paid homage to this bringer of life. We bowed to dawn and rested at dusk. We celebrated the sun's return at winter solstice festivals, when days would lengthen again. Even monotheistic religions kept echoes of sun worship, halos around saintly heads, Sunday as a holy day. The sun was our first clock and calendar, a golden heartbeat to measure our days.
Yet, for all its importance, the true nature of the sun remained a mystery to our ancestors. They saw a bright disk that moved and gave heat, but what it was, a chariot wheel, an eye of a god, a hole into the realm of fire. No one knew. Still, they revered it rightly as the great sustainer. They intuited that without the sun's daily presence, the world would be cold and dead. In their myths, the sun was often benevolent, but sometimes fickle or wrathful, a reflection of how its light could bless crops or, in drought, become a searing curse. Even today, if you've ever stood at dawn and felt the first rays warm your face, you can sense that ancient awe. The sun touches something primal in us. It's no wonder early humans worshipped it. They were reaching out to understand and thank the very thing that made their lives possible, from myth to science. In time, humanity's curiosity outgrew our myths. We began to seek a more concrete understanding of the sun. Gazing up, we asked not only who carries the sun across the sky, but what is the sun, really? Our journey to the answer spanned centuries. It led us from seeing the sun as a unique heavenly jewel to recognizing it as one among countless stars, and ultimately to uncovering the nuclear fire at its heart. It started with a radical idea that the sun, not Earth, was the center of things. Renaissance astronomers like Copernicus and Galileo dared to put the sun at the center of our solar system, dethroning Earth. This heliocentric model slowly overturned old cosmic orders, and with them, the special pedestal of our sun as something apart from the stars. In 1610, Galileo turned his telescope to the sun and saw dark blemishes crossing its face, sunspots. The discovery that the sun had spots and that they moved, showing the sun's rotation, was shocking. It meant our perfect heavenly light had imperfections. The sun was not a flawless god, but a dynamic, changing sphere. Galileo's observations, nearly blinding work in an era without proper filters, marked humanity's first scientific look at our star. As the centuries turned, more questions arose. What was the sun made of? How could it burn so brightly for so long? By the 19th century, even as scientists catalogued the sun's spectrum and found new elements, the sun's power source remained an enigma. Some theorized it was a burning coal or contracting gas, but calculations showed chemical fire or gravity alone could not sustain the sun for millions of years, let alone the billions required by Earth's geology. The sun simply put out too much energy. The answer arrived in the 20th century. The sun shines by thermonuclear fusion. In its core, light elements are fused into heavier ones, releasing prodigious energy. In essence, the sun is a gigantic nuclear reactor. This realization dawned slowly.
Scientists like Arthur Eddington first guessed it, that the pressures at the sun's center could force hydrogen atoms to merge into helium. Later, others worked out the details of those reactions. At long last, we understood. The sun was not a divine flame or a burning ember of creation. It was a star, a common type of star, powered by extraordinary processes. The gulf between our sun and the stars in the night sky closed. They were the same kind of thing. Our sun is just our star, the one we happen to live next to. This was a humbling shift. The sun went from being the singular light of our existence to one of perhaps 100 billion lights in our galaxy. The word sun itself simply means any star that has planets in orbit. Astronomy taught us that each star in the sky is another sun for someone, and perhaps each sun in turn could warm other worlds. The universe became both bigger and more intimate. We found kinship between our sun and the countless stars shining out there. So our sun is a typical star, but it is also unique to us. It is our sun, the anchor of our solar system, the gravitational linchpin that holds 8 planets, dozens of dwarf planets, millions of asteroids, and trillions of comets in its family. It contains 99.8% of all the mass in the solar system. All the planets, moons, and debris are mere crumbs from the sun's table. This brilliant sphere dominates our cosmic neighborhood. Today, instead of worship, we show reverence through exploration. We study the sun with a fleet of spacecraft and a cadre of telescopes. We have learned more in the last few decades than in all of human history before. Yet the more we uncover its scientific secrets, the more our sense of wonder grows. The sun is not a simple ball of fire. It is a complex living system with a heartbeat and moods, with mysteries and surprises still in store. We have traded mythic poetry for factual poetry, one might say. The truth of the sun, as a star powered by fusion, variable and even violent, is as awe-inspiring as any legend. With our modern understanding, we can tell the sun's story from its birth among the stars, through its present life, giving glow, and on to its far future fate. We can connect the nuclear reactions in its core to the warmth on our skin. We can appreciate how the sun's tantrums create ethereal auroras on Earth, and how, someday, the sun will transform and force life as we know it to change or perish. This is the saga of our sun, one star in an endless sea, yet everything to us. Now, let us journey into the life of the sun itself. Let us peel back the layers of our star, travel to its core, and ride the energy outward. We will watch the sun's surface seethe and erupt. We'll follow its influence across space to Earth and beyond. We'll look back to the sun's birth and forward to its death. And in doing so, perhaps we'll come to see the connection between that nuclear furnace and the beat of our own hearts, born of cosmic clouds. Every star has a story that begins in darkness. The sun's tail starts around 4.6 billion years ago in a cold, diffuse cloud of gas and dust on the outskirts of the Milky Way galaxy. Picture a vast nebula, light years across, full of hydrogen, helium, and faint traces of heavier elements. For ages, this cloud drifted quietly. Then something happened to disturb its peace. Perhaps a shockwave from a distant supernova slammed into it, or maybe 2 clouds collided. Whatever the trigger, it caused a region of the cloud to compress. Within that region, gravity took hold. A denser clump drew in more and more material, growing denser and heavier in a runaway process. As the gas fell inward, it began to spin, an ice skater pulling in her arms, rotating faster and faster. The collapsing clump flattened into a swirling protoplanetary disk, like a cosmic whirlpool, with most of the mass collecting at the center. That center grew ever hotter and denser as gas piled on. This was the protostar that would become our sun, still shrouded, not yet shining by its own light, but getting warmer and warmer. Around this infant protostar, the remaining disk of gas and dust would eventually clump to form planets, moons, and asteroids, the embryonic solar system. But at this early stage, all attention is on the burgeoning star, child, at the disk's core. As more mass crushed in, the protostar's core pressure skyrocketed. When the core reached about 15 million degrees Celsius, a profound transformation occurred. Hydrogen nuclei began to fuse. At first, it was just a trickle of fusion reactions sparking to life, but soon a threshold was crossed. The protostar effectively ignited in a sustained way. The inward crush of gravity was met by the explosive outward pressure of new energy. The darkness of the collapsing cloud was pierced by the first true starlight of our sun. It was born, a full-fledged star, now stabilizing into the long, steady burn of its youth. If we could have witnessed it then, we'd see a new star appearing where none had shone before, hidden deep in its natal cloud until its light blew away the cocoon. Perhaps it glowed a bit bluer and larger at first, shedding excess heat, then settled to the yellow-white we know. Our sun joined the cosmic landscape as one more pinprick of light in the galaxy. Around it, the leftover disk began to cool and condense. Within tens of millions of years, that disk formed the planets, including Earth, making the sun not only a star, but the center of a solar system. Interestingly, our sun wasn't born alone. Star formation often happens in clusters. Multiple stars form from different clumps in the same giant cloud. Our sun likely had sibling stars born in the same stellar nursery. For a few 100 million years, they might have been loosely bound, a cluster of suns drifting together. But over time, they scattered across the Milky Way, each going its own way. Somewhere out there in the galaxy, far from us now, there may be stars that once twinkled alongside the infant sun before destiny separated them. Now they are just anonymous stars in the night sky, their shared origin with our sun obscured by time and distance. So the sun's birth was both a solitary emergence from darkness and part of a communal genesis of many stars. From gravity's pull and nature's want of equilibrium, a star was born, the furnace was lit, and in that lighting, the stage was set for everything to come, the formation of Earth and the eventual spark of life in the sun's warm glow. The hearth of fusion, at the core of the newborn sun, and still today, in the mature sun, an astonishing process unfolds: thermonuclear fusion. This is the engine of the star, the secret of sunlight. Yet for all its technical sound, we can think of fusion in human terms. It is the sun's heartbeat, the rhythmic source of energy that keeps it alive. Deep in the sun's center, the conditions are almost inconceivable. The pressure is millions of times the atmospheric pressure on Earth. The temperature is around 15 million degrees C. The hydrogen gas that composes most of the sun is crushed so tightly that it becomes a dense plasma, atoms stripped of electrons, nuclei packed shoulder to shoulder. In this extreme environment, hydrogen nuclei, which are simply protons, are forced close enough together to overcome their natural repulsion. When two protons slam together hard enough, they can stick and transform, ultimately creating a helium nucleus out of 4 hydrogen nuclei through a series of reactions. In that alchemy, a tiny bit of mass is lost and converted to pure energy. This is happening constantly in a chain reaction known as the proton fusion cycle. Every second, the sun's core fuses about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, converted to energy as radiant light and heat that eventually makes its way out of the sun. 4 million tons of matter turned into energy every single second. It's a number almost too large to grasp. It's like detonating billions of nuclear bombs each second just to produce the sunlight we find so gentle here on Earth. How can we imagine this furnace? perhaps as a stellar heart, throbbing out energy, or as a vast forge where the simplest element, hydrogen, is forged into helium, like an eternal smithy. Or think of it as a boiling cauldron of creation, where matter and energy are freely interchangeable. The core is only about a quarter of the sun's radius, but it holds nearly half the sun's mass, densely packed and actively burning. It is here that the sun's life is decided. So long as there is hydrogen to fuse, the sun will shine steadily. Fusion in the sun is a surprisingly subtle dance, not a runaway explosion. The star's self, gravity contains and regulates it. If the core produces a bit too much energy, the core will expand slightly, cooling and slowing the fusion rate. If it produces too little, the core contracts, heating up and boosting fusion. This feedback keeps the sun in an equilibrium that has persisted for billions of years. In this way, the sun is stable, a gently humming engine rather than a bomb. The heat flowing outward provides pressure to counter gravity inward. A beautiful balance. Gravity compresses, fusion energizes. One tries to collapse the star, the other tries to blow it apart, and in the middle the sun holds steady, like a suspended ball in a fountain stream. While hydrogen fuses to helium in the core itself slowly accumulates helium ash. Over the sun's lifetime, helium has been building up inside. But the sun has so much hydrogen and burns it relatively slowly that even after 4.6 billion years, it's nowhere near running out. Our sun is comfortably middle-aged, still rich in fuel for about another 5 billion years of hydrogen burning. It's mesmerizing to think. Every photon of sunlight, every beam that warms your skin began as an act of nuclear fusion in the sun's core. Each one was born in a flash of two atoms becoming one, releasing energy. The sunlight is literally the product of mass turned into energy deep within our star. The sun's core is a closed realm, hidden from direct view. Yet it is the very definition of vitality for the sun. If we call the sun the heart of our solar system, it's apt because within the sun lies a heart of its own, pumping out the light that feeds the planets. This fusion hearth is not static. It subtly pulses, not in dramatic throbs, but through waves and oscillations that ring through its interior. Through a field called helioseismology, scientists have detected sound waves echoing inside the sun, caused by bubbling convection and other processes. By studying these solar seismic waves at the surface, we infer details about the core's conditions. In essence, we can listen to the sun's heartbeat and learn its rhythm and structure. It's like ultrasound for a star, listening to its ringing to map its insides. And what have we found? That the sun's core rotates a bit faster than its surface, and that it's maybe a touch hotter or cooler in spots than expected, but by and large, our models of fusion hold true. With the core burning steadily, the sun has entered what's known as the main sequence phase of its life, the long, stable period in which a star fuses hydrogen to helium. For a star of the sun's mass, this period lasts about 10 billion years. Our sun is nearly halfway through that allotment. During this time, it changes only gradually, growing slightly brighter over eons as helium accumulates in the core. But for now, the sun shines with a steady golden consistency that has nurtured life on at least one world. Journey of light. Consider now a single photon, a particle of light, born in the sun's core. It begins its life as a high-energy gamma ray emitted from a fusion reaction. In that first moment, it's a blazing bit of energy flying outward, but its journey to escape the sun is anything but straightforward. The sun is incredibly dense in its interior, and this newborn photon's path is immediately halted by a collision with a nearby proton or electron. It gets absorbed and re-emitted or scattered in a random direction. It zigzags and ricochets through the crowded interior like a pinball in an infinite machine. The sun's interior has layers like an onion. From the core Out to about 70% of the sun's radius lies the radiative zone. Here, the dominant mode of energy transfer is by radiation, photons carrying energy outward, but it is a slow diffusion process. The photon we imagined will undergo an enormous number of scatterings in the radiative zone. It bounces a short distance, hits a particle, gets sent in a new direction, maybe even back inward, then out again, over and over. It performs a drunken, random walk toward the surface. The distances between collisions grow longer as the gas gets thinner farther out, perhaps only a fraction of a millimeter near the core between collisions, stretching to a few centimeters near the radiative zone's outer edge. It is an epic and tedious journey. How long does it take for a photon to get out? Ironically, something that travels at the speed of light can take on the order of thousands or even hundreds of thousands of years to escape the sun. Estimates vary, but by many accounts, the sunlight that reaches your eye today began its trip in the sun's heart when humanity was in its infancy or before. In a poetic sense, the daylight illuminating an ancient Egyptian carving might have been generated around the time the sun's energy currently warming us was starting its long march outward. The sunlight is ancient by the time it emerges. In contrast, once it's free, it only takes a brief 8-minute sprint across space to reach Earth. Thus we say, every sunrise is powered by ancient light. Eventually, our photon reaches the outer 30% of the sun's interior, the convection zone. Here, the density has dropped and the temperature gradient steepened such that gases can't transfer heat by radiation alone. They begin to circulate like a boiling pot of water. Hot plasma near the radiative zone rises toward the surface, cooling as it goes, then sinks once it has given off its heat, only to be reheated and rise again. These convection currents are enormous, each cell the size of a continent or larger. In cross-section, they look like granules or kernels. Indeed, if you look at the sun's surface with a high-powered telescope, you see a granulation pattern, a carpet of bright blotches with darker boundaries. Those bright blotches are the hot tops of convection cells where material is upwelling. The dark outlines are cooler, sinking material. The scale is staggering. Individual granules are on the order of 1,000 kilometers across. For our photon, being caught in the convection zone is like catching an express elevator after wandering in a maze. The energy gets swept up by the moving plasma and ferried upward much more directly. Within days or weeks, a blob of plasma can rise from the bottom of the convection zone to the visible surface, carrying its photon energy with it. When that plasma finally reaches the surface, the photosphere, it radiates the energy away as new photons of mostly visible light. Our original photon might have been absorbed and its energy redistributed into many lower energy photons by now. By the time energy leaves the sun, it is mostly in the form of visible light with a spectrum peaking in the greenish yellow, perfect for our eyes, which evolved under this light. In essence, the sun converts the furious gamma rays of the core into a brilliant white light at the surface, a bit like allowing scalding steam to cool into warm water by the time it touches you. The photosphere is what we typically refer to as the sun's surface. Although being gaseous, the sun has no solid surface. It's the layer where the plasma becomes transparent enough for photons to finally escape into space. It's only a few hundred kilometers thick, razor thin compared to the sun's 700,000 kilometer radius. The photosphere's temperature is about 5,500 degrees in its upper layers, cooler than deeper inside, but still hot enough to glow bright. This is the light we see. When you safely project or filter an image of the sun, the features you observe, the mottled granulation, any sunspots, reside in the photosphere. As our photon escapes the sun and zips into the solar system, another ghostly traveler flies outward too, neutrinos. These nearly massless particles are produced in astronomical numbers by fusion reactions. Unlike photons, neutrinos interact so weakly with matter that they stream straight out of the sun's core and into space almost unhindered. reaching Earth in just over 8 minutes. Trillions pass through your body each second, unnoticed. They are like telegrams from the sun's core, confirming fusion is ongoing. We have built giant underground detectors to catch a handful of these elusive particles, and indeed, we have detected them, verifying that the sun's core is doing what our theory says. Neutrinos are essentially a direct line of sight to the sun's core, whereas photons only show us the surface. They've told us that the sun's output hasn't changed drastically in at least 100,000 years, and that our fusion calculations are correct within a few percent. So now, after an arduous journey, the energy birthed in the solar core has made it out. The sun's light is free, radiating into space in all directions. A minuscule fraction of it will intersect Earth, providing daylight and sustenance. The rest travels on, maybe to light up other planets, or just to disperse into the void. This continuous flow of energy from core to surface to space is the lifeblood of the sun. It is as if inside the sun, a story is written in energy, and that story travels for millennia to emerge as the light that then writes a chapter in the story of life on Earth. The many hues of sunlight. Step outside on a clear day and look at sunlight. To our eyes, it looks bright and roughly white or golden, depending on the time of day. But sunlight is not a single color or type of light. It is a symphony of many wavelengths of electromagnetic radiation, from high energy ultraviolet to visible colors to low energy infrared and beyond. The sun is often depicted as yellow in drawings, but in truth, the sun emits all colors of visible light blended together, which our eyes perceive as white. Our atmosphere can make the sun look yellow, orange, or red at times by scattering away the shorter wavelengths. But in space, the sun shines a near white. If we pass sunlight through a prism, it fans out into a rainbow, the solar spectrum. Every color from violet through red is present, fading seamlessly one into the next. This is the sun's visible fingerprint. Sprinkled in that rainbow, scientists have found dark lines, the Fraunhofer absorption lines, where elements in the sun's cooler outer layers absorb specific colors. By decoding those spectral lines, we learned which elements abound in the sun. Hydrogen and helium, overwhelmingly, with traces of almost every other element present in smaller amounts. In fact, those dark lines in the solar spectrum led to the discovery of helium in 1868. It was seen in the sun before it was found on Earth. The sun thus gave us helium, an element that remained hidden on Earth until later. But the sun's spectrum extends far beyond what our eyes can see. Ultraviolet radiation from the sun, invisible to us, is present in sunlight and carries more energy per photon than visible light. Most UV is fortunately blocked by Earth's ozone layer and atmosphere, but enough reaches the ground to give you a suntan or sunburn, a daily reminder that the sun outputs rays that can be both life-enabling and harmful. At even higher energies, the sun emits X-rays and even gamma rays, especially during solar flares, but those do not penetrate our atmosphere. On the other end, the sun emits plenty of infrared radiation, experienced by us as heat. Step into a patch of sunlight on a cool day and feel warmth on your skin. That's IR at work. Roughly half of the solar energy reaching Earth's surface is in the infrared. It's what warms the ground, oceans, and air. Plants reflect a lot of near-infrared, which is why they appear bright in infrared photography, but they eagerly absorb visible light for photosynthesis. The sun also emits radio waves, though relatively weakly in continuous spectrum. However, during solar flares or plasma oscillations, strong bursts of radio waves can occur, which we can pick up with antennas. Meanwhile, just below visible light is near ultraviolet, and just above violet is extreme ultraviolet. The sun emits those from its hotter regions, like the chromosphere and corona. Viewing the sun in different wavelengths reveals different stories. In ultraviolet, we see the chromosphere and lower corona, as a dynamic network of loops and flashes. This is how satellites like SOHO and SDO image the sun's atmosphere and catch flares or eruptions. In visible light, we see the familiar yellow-white photosphere with sunspots, faculae, and granulation. In infrared, we can probe cooler features and sometimes see deeper into sunspot regions, and also observe the solar limb darkening effect clearly. In EUV and X-rays, we see the million-degree corona blazing from active regions, coronal loops, and coronal holes. In radio, we can study the sun's corona and even below the surface via radio emissions and detect burst events from flares. This broad spectrum underscores that the sun isn't just a static bulb of white light, but a multifaceted powerhouse. It also highlights how the sun affects Earth on many levels. UV shapes the upper atmosphere chemistry. Visible light fuels life and drives weather by heating Earth's surface unevenly. IR provides direct heat and is key to the greenhouse effect that keeps Earth warm. Interestingly, the sun's spectrum peaks in visible light, and not by accident. Our eyes evolved to be sensitive to the sun's peak output, and Earth's atmosphere has a window of transparency in the visible range. If the sun were a cooler red dwarf, peak output would be in infrared, and perhaps eyes on a planet there might evolve to see IR, or if hotter, eyes might see more UV or blue. And then there's invisible sunlight beyond the EM spectrum, neutrinos and the solar wind of charged particles. Both could be considered outputs of the sun in a broader sense. Solar wind shapes Earth's magnetosphere and is the cause of auroras, as we'll discuss. And neutrinos provide insight into the core. The solar constant is about 1,361 WD. This is what powers essentially all surface phenomena on Earth, from winds to ocean currents, to the water cycle and life itself. It's remarkably stable, varying only 0.1% over the 11th year cycle, and maybe up to 0.3% over centuries, if at all. The sun is more stable than many stars, which is fortunate for us because even a few percent variation could profoundly affect climate. That stability is one reason complex life could flourish on Earth. Our sun is a well-behaved star, not prone to large swings in luminosity. To sum up, the sun wears many colors. It emits a broad spectrum from radio waves to gamma rays. We see just a sliver, but modern instruments have expanded our vision. This multi-wavelength view has turned the sun from a blinding disk into a rich landscape of features. A calming white photosphere here, a violent UV flare there, a shining X-ray corona above. It reminds us that reality is often beyond human senses, and only by extending them do we fully appreciate the sun's grandeur. The next time you notice the golden light of late afternoon or enjoy the colors of a sunset, remember that this show is the result of the sun's rays interacting with our atmosphere. The reds and oranges of sunset happen because blue light has been scattered out, leaving the warm tones to travel through thick atmosphere to your eyes. It's a daily demonstration of the sun's spectrum and Earth's filtering, a touch of cosmic physics in an everyday experience. The sun's surface and atmosphere. The word surface is a bit misleading for the sun, since it has no solid crust. But when we say surface, we mean the photosphere, the visible disk from which light escapes. Just above the photosphere, the sun has an atmosphere of its own, layers of gas that are even more rarefied, where fascinating and sometimes puzzling things occur. Immediately above the photosphere lies the chromosphere, a region a few thousand kilometers thick. Normally, the chromosphere is hard to see because the photosphere's glare overwhelms it. It reveals itself in certain wavelengths or during solar eclipses as a thin pinkish rim around the sun. During a total eclipse, just as the sun is almost completely covered, observers often see a red flash or fringe. That's the chromosphere emitting light, notably the red glow of hydrogen gas. early spectroscopists called it the flash spectrum.
The chromosphere is a dynamic, fiery layer. It's populated by spicules, narrow, spike-like jets of plasma that shoot up from the photosphere into the chromosphere and last only minutes. Thousands of spicules are active at any time, giving the chromosphere a jagged, fur-like appearance in certain filters. The chromosphere is also threaded with filaments and plages. The temperature in the chromosphere actually rises with height, from about 4,500 K at the bottom to perhaps 20,000 K or more at the top. This is already a clue of some extra heating beyond simple radiative loss. Above the chromosphere, there's a thin transition region only a few hundred kilometers thick, where the temperature skyrockets from tens of thousands to nearly 1,000,000 Kelvin. Immediately above that is the corona, the sun's outer atmosphere, which extends millions of kilometers into space. The corona is breathtaking. During a total solar eclipse, it's that pearly white crown we see encircling the black lunar silhouette. It's made of extremely hot, tenuous plasma. The corona is actually far less bright than the full moon. We can see it in eclipse only because the moon blocks the overwhelmingly brighter photosphere. One of the longest-standing puzzles in astrophysics is the coronal heating problem. Why is the sun's corona so hot when the sun's surface is relatively cool? Typically, if you move away from a heat source, temperature drops, like walking away from a fire. But above the photosphere, at first it drops. Then it leaps upward in the corona. It's as though you walked away from a campfire, and suddenly the air got scorching hot, far beyond the flames. Scientists suspect the sun's magnetic field is the culprit. The sun's surface and interior churn with electrically charged plasma, which twists magnetic field lines. These fields carry energy upward. There are a few ideas on how they deposit heat. Magnetic reconnection. Tangled magnetic field lines in the corona can snap and rejoin, releasing energy as heat. This could heat pockets of plasma to high temperatures. Waves. The turbulent motions of the photosphere might send upward Alfvén waves or other magneto-hydrodynamic waves that carry energy. When these waves reach the less dense corona, they could dissipate their energy as heat. Microjets or current sheets. Various small-scale dynamic phenomena in the lower corona might rapidly pump energy into coronal plasma. The Parker Solar Probe is actually gathering data relevant to this, diving into the corona to measure fields and particles directly. Early results have observed strange zigzag switchbacks in the magnetic field and bursts of plasma, providing clues. The solar orbiter has imaged omnipresent tiny flares on the solar surface, which might be part of the heating story. The corona is structured by the magnetic field. Above active sunspot regions, you get bright coronal loops in X-ray and EUV images, arches of plasma confined by magnetic lines, glowing at millions of degrees. In polar regions, or places with open field lines, you get coronal holes, which appear dark in X-ray EUV because they're cooler and less dense. These are sources of fast solar wind streams. The corona continuously expands into space, creating the solar wind. At some point, the plasma becomes so thin that particles escape the sun's gravity. That's the beginning of the wind. The boundary where the sun's atmosphere transitions to solar wind is not sharp. Essentially, the corona is the solar wind's birthplace. Now moving back inward, the chromosphere and corona aren't static shells. They are in constant flux. Solar flares often manifest as bright ribbons in the chromosphere and dazzling loops in the corona. When we monitor the sun in H-alpha, we primarily see chromospheric structures, filaments, plages, flares at their origin, and spicules at the limb. The photosphere, though cooler than the layers above, is where sunspots reside, and those spots have intense magnetic fields that shoot up into the corona, linking the layers. Think of sunspots as the visible feet of magnetic flux tubes that rise into the corona. Energy stored in those tubes can be released higher up. Our vantage from Earth's surface usually just shows us the bright photosphere.
But with specialized solar telescopes and space observatories, we've managed to study these atmospheric layers intimately. The Solar Dynamics Observatory, for example, continuously images the sun in multiple wavelengths, giving us a 24/7 view of the chromosphere and corona dancing and flaring. It's inspiring that a total solar eclipse, one of nature's grand spectacles, was the key for humans discovering the chromosphere and corona well before the space age. During the eclipse of 1868, Jules Janssen and Norman Lockyer independently identified that mysterious yellow spectral line. During the eclipse of 1869 and others, observers noted green lines in the corona. Eclipses basically shouted to us, "There's more to the sun than meets the eye." Now we have artificial eclipses and advanced filters to monitor these layers routinely. We've directly imaged spicules, measured chromospheric magnetic fields, and observed the corona in X-ray movies over decades. Yet, even with all this, the solar atmosphere holds mysteries. We still debate exactly how the corona gets so hot. We don't fully understand the engine behind the 11th year cycle. We have difficulty predicting flares. We can see a region is ripe, but exactly when or how big a flare will go off is not yet predictable. We've realized the sun's atmosphere can even sing. It's filled with oscillations. The corona has waves and oscillatory phenomena that we can detect as periodic brightness changes. The sun is not quiet up there. It's ringing with acoustic vibrations, albeit far too thin to carry sound that we could hear with ears. Lastly, consider the scale. The corona seen during an eclipse extends several solar radii, but the influence of the sun's atmosphere actually reaches far beyond, effectively out to where the solar wind meets the interstellar medium. In that sense, the sun's atmosphere encompasses all the space where its particles and magnetic field extend. Earth orbits well within this realm, swimming in the solar atmosphere. We're effectively inside the sun's extended atmosphere all the time, in the solar wind's bubble. That's an astounding thought. We live inside the outer atmosphere of our star. So, summing up the sun's atmospheric layers: photosphere, 100 kilometers thick, 5,800 K. What we see as the surface: sunspots, granules, faculae live here. Chromosphere, few thousand kilometers thick, 10,000 K. Reddish glow in H alpha, home of spicules, filaments, magnetic network. Temperature rises with height. Transition region, very thin. Temperature shoots up to 1 million K. Corona, millions of kilometers, are 1,3 million K. Thin plasma shaped by magnetic fields, source of solar wind. Each layer is physically part of the sun, but conditions change so radically that we treat them as distinct zones. And through these layers, the sun's magnetic field is the scaffolding and the agitator. The sun's magnetic heartbeat. Peering at the sun over weeks and years, astronomers long ago noticed a curious pattern. The number of sunspots on the sun's face varies in a cycle, roughly every 11 years. At times, the sun's face is nearly clear, maybe a tiny spot, or none at all for days. This is solar minimum, the quiet phase. Years later, dozens of spots speckle the sun, some growing big enough to see without a telescope as tiny blemishes. That's solar maximum, the active phase. Then the activity wanes again. This rise and fall is the famous sunspot cycle. Sunspots themselves are regions where the sun's surface is cooler than the surroundings. A typical large sunspot might be around 4,000 K in its dark core, compared to 5,800 K in the bright photosphere. Spots often come in pairs or groups, with opposite magnetic polarity. Essentially, they are like north and south magnetic poles, poking through the photosphere. One spot will have magnetic field coming out, and the other nearby with field going in, connected by loops of magnetism above. Counting sunspots by eye and later by camera, people realized they follow this quasi-11th year oscillation. Around 1850, Rudolf Wolf pieced together historical records and came up with a sunspot number index that revealed this cycle. Today, we're in cycle 25. For perspective, cycle 24 peaked around 2014 with a modest number of spots, and then an extended quiet period occurred around 2018-2019. Now cycle 25 is ramping up, likely to peak around 2025 or 2026 with a moderate number of spots. The sunspot cycle is not perfectly regular. Some cycles are 9 years, some 14, but average have on 11. Also, the amplitude varies. Some cycles in the 20th century were very strong, while some in the 19th were weaker. The 17th century Maunder minimum was an extreme case. Very few sunspots were recorded from about 1645 to 1715, a period that coincided with cooler climate in Europe. There's evidence from carbon in tree rings that other grand minima occurred in the past. So the sun's cycle itself modulates on longer timescales. What causes the cycle? The root is the sun's magnetic dynamo, the mechanism by which the sun generates its magnetic field. The sun rotates and has huge convective motions in its outer layers, plus likely a shear layer at the base of the convection zone. The interplay of these motions stretches and twists magnetic field lines inside the sun. Roughly every 11 years, the field gets so twisted that it resets. The sun's global magnetic polarity flips. It then takes another 11 years to flip back, so the full magnetic cycle is 22 years. Sunspots are a direct manifestation of this magnetic cycle. Early in a cycle, the first spots of the new cycle appear at mid-high solar latitudes. They often come in with reversed polarity compared to last cycle's spots. As the cycle progresses toward maximum, spots appear in greater numbers and at lower latitudes. Near the peak, you might see spots even 5,010 degrees from the equator. After maximum, as the cycle decays, spots get scarcer and cluster near the equator. Then it resets. No spots at the equator, and new spots of opposite polarity start popping up back at high latitudes for the next cycle. If you plot latitude of spots over time, you get the butterfly diagram. 2 wings per cycle descending toward the equator. Sunspots come and go over days to weeks. They often emerge, grow, break apart, or explode. They often appear in active regions, an area with complex magnetic structure, including multiple spots, faculae, plages, etc. Those are the ones likely to produce flares and CMEs. During solar maximum, the whole sun is magnetically disturbed. The corona is full of bright active region loops. There are more flares, and the sun's overall UV and X-ray output is higher. At solar minimum, the corona is simpler, with big coronal holes at the poles and few bright loops, and the sun's X-ray brightness can drop to nearly nothing. It's important to note the cycle isn't perfectly uniform. Sometimes big sunspots or storms happen in the decline phase, etc. But overall, more sunspots means more potential for solar storms, and vice versa. Now, why should we care about the sunspot cycle? It's not just academic. It drives the space weather environment around Earth. During high sunspot years, we get more frequent solar flares and CMEs, meaning more auroras and geomagnetic storms on Earth, as well as more radiation hazards for satellites' astronauts. During low years, space weather is quieter, but interestingly, cosmic ray flux at Earth increases. Also, the outer atmosphere of Earth cools and contracts during solar min due to less EUV heating, which can affect satellite orbits. So even earthly systems respond to the cycle. For example, the upper atmosphere density difference between solar max and min is significant for orbiting objects. Also, one's view of the polar aurora oval expands in solar max and shrinks in solar min. Radio communications on Earth are affected by the cycle too. HF radio propagation tends to be better around solar max because the ionosphere is more ionized, while during solar mine certain frequencies propagate poorly. So the sun's 11th year heartbeat sends ripples through our technology and environment. On the sun itself, the cycle orchestrates phenomena. The polarity of sunspots flips each cycle. The number of prominences, flares, sunspots, faculae all follow the cycle. Even the solar poles reverse their magnetic field at each maximum. Yes, the sun's north and south magnetic poles flip around the time of sunspot peak. That's when the global field is weakest and messy, then a new polarity builds and settles by the next min. To get a little deeper, when the sun approaches minimum, often the last spots of the old cycle linger near equator. But already by then, new spots from the next cycle might have appeared at high latitudes. So cycles actually overlap slightly. We identify cycles by when the old spots mostly vanish and new ones dominate. Magnetic oddities occur too. Occasionally, there are short breaks in cycles or irregularities. We don't fully understand the sun's long-term magnetic modulation. It might have 50-year, 100-year variations. Some predict another grand minimum could occur, but that's uncertain. The cycle also has asymmetries. Typically, one hemisphere of the sun leads or dominates in a given cycle. For instance, the north might erupt earlier and have more spots one cycle, and the south might dominate the next, etc. This is an active area of research, trying to see patterns in these differences. Now, what exactly are sunspots in physical terms? They are concentrations of strong magnetic field on the order of 0.1 to 0.4 Tesla. For comparison, Earth's surface magnetic field is about 0.0005 Tesla, so sunspot fields are thousands of times stronger than Earth's field. These fields suppress convection locally, so less hot material rises, and the area cools relative to surroundings, hence looks dark. A sunspot often has a dark core and a surrounding mottled, lighter grey area with filamentary structure. Those penumbral filaments are somewhat convective flows channeled by the field. Sunspots can be as small as a few hundred kilometers or as large as 50,000 kilometers across. Galileo's drawings show some large ones visible to the projection technique he used. The biggest tend to appear around solar max. Sunspots often appear in pairs, roughly east, west of each other. One will be magnetically north, the other south. In the next hemisphere, the polarity orientation is reversed. In the next cycle, all that flips. So, summing up, the sun has a magnetic heartbeat of 11 years. It's like a slow pulse, where every beat inverts the field. With each beat, the sun goes from calm to active to calm again. At the peak, it shows its magnetic muscles via sunspots and flares. During the lull, it's magnetically catching its breath, reorganizing for the next wave. We have kept count of these beats for centuries now, and while each has its own character, the persistence of the cycle is a remarkable feature of our star. Many stars show magnetic cycles too, but the sun's is the one we have in most detail. Understanding the cycle isn't just for curiosity. It helps anticipate periods of greater solar storm risk, plan satellite launches. It also feeds into climate discussions. Tiny solar output variations might have slight influence on climate, though current climate change is dominated by anthropogenic effects. This magnetic heartbeat will continue for a few billion more years, but as the sun evolves into a giant later, it will likely become more erratic or different. Red giants can have magnetic fields, but often not cycles like the sun's. That's far ahead though. For now, we are mid-cycle in cycle 25. In a few years, we'll likely see a lively sun peppered with spots and laced with flares. A good time for aurora watchers. Then it will calm down again. The dance goes on. Storms on the sun. The sun's magnetic cycle not only brings dark spots but also violent outbursts. When magnetic energy that's been stored in twisted field lines suddenly releases, the sun experiences storms, primarily solar flares and coronal mass ejections. These are the most dramatic manifestations of a star's magnetic wrath, and they can have direct consequences many millions of kilometers away on Earth. Solar flares are essentially gigantic explosions in the sun's atmosphere. In minutes, A localized region on the Sun can release as much energy as billions of nuclear bombs. A flare brightens across the spectrum. Intense X-rays and extreme UV pour out. Visible light can even increase in what's called a white light flare, and radio waves and gamma rays might be emitted too. Flares are classified by their X-ray brightness as observed by Earth orbiting satellites. The classes are A, B, C, M, X, each a step up by factor of 10. A is very small, B small, C moderate, M medium, large, X large. Within each letter class, they use a numeric scale from 1 to 9. For example, an X2 flare is twice as strong as X1 and 4 times as strong as an M5. The biggest flares recorded by modern instruments were about X28 in 2003. The Carrington event flare in 1859 is inferred to be perhaps X-class in the 30s, though direct measurement didn't exist. What triggers a flare? Magnetic reconnection is the key. Imagine magnetic field lines arching out of a sunspot pair like loops. If these lines become stressed and tangled enough, they can snap and reconnect in a lower energy configuration, like a rubber band breaking. When that happens, all the energy that was stored in the twist of the magnetic field is suddenly released as heat, light, motion, and particle acceleration. The plasma in that region gets superheated. Electrons are hurled to near light speed, spiraling along field lines, and protons and heavier ions are likewise accelerated. In images, a flare often appears as a bright flash or set of ribbons in H, alpha, or UV on the solar disk. Then you see post-flare loops, graceful glowing arcs in the aftermath as the hot plasma cools and settles in magnetic loops. Flares can happen without a CME, especially smaller ones, but big flares often coincide with a CME. Coronal mass ejections are colossal eruptions of solar plasma and magnetic field into space. Think of it as the sun belching out a piece of its atmosphere. A CME typically involves a twisted flux rope of magnetic field that suddenly ejects, carrying with it billions of tons of coronal gas. CMEs travel at speeds from a few hundred km/s to up to 2 to 500 pounds/km/s for really fast ones. At Earth's distance, that's about 1 to 3 days of travel. We often see CMEs with coronagraphs, a halo or a bright loop structure expanding away from the sun. If a CME is coming toward Earth, we might see a halo CME. Many strong flares have an associated CME, but not all. And you can have a CME without a big flare if a region's field slowly destabilizes and erupts without a sudden flash. Now, when these storms occur, what do they do to Earth? This brings us to space weather effects. Electromagnetic radiation from a flare, X-rays, and UV arrive in 8 minutes at Earth. They ionize the upper atmosphere. This can cause radio blackouts for HF communications. GPS signals can be degraded. Essentially, a strong X-class flare can temporarily deafen our ionospheric radio wave propagation on the sunlit side. This is called an R event in NOAA space weather scales. The effect typically lasts an hour or a few hours as the ionosphere gradually recombines. Solar energetic particles. Some flares accelerate particles, mainly protons, to near relativistic speeds. These proton storms can arrive in tens of minutes to hours after the flare. These particles pose a radiation hazard. They are deflected by Earth's magnetic field for the most part, but some get funneled toward the poles, causing a shower of ionization in the atmosphere. On high-altitude polar flights, this can increase radiation dose to passengers and crews. For astronauts, especially outside the ISS, it can be dangerous without shelter. SEPs can also physically damage satellites, penetrating electronics, causing bit flips, charging surfaces leading to discharges, degrading solar panels and materials. NOAA calls these S events, scaled S1 to S5,
An S3 or above can prompt airlines to reroute polar flights to lower latitudes. During one event in 2012, some airlines did this as precaution. Coronal mass ejection impact. When the CME cloud arrives a day or two later, it's the geomagnetic storm time. The CME plasma carries embedded magnetic fields. If the magnetic field in the CME is oriented southward, when it hits Earth, it couples strongly with Earth's northward field. This injects energy and plasma into our magnetosphere and triggers a geomagnetic storm. A geomagnetic storm is essentially a global disturbance in Earth's magnetic field. It causes beautiful auroras. It also can induce electric currents in long conductors on the ground, notably power lines and pipelines. In extreme cases, these currents can overload transformers in power grids, causing blackouts. The classic example, the Carrington event of 1859, caused telegraph lines to spark and even caught telegraph paper on fire. Operators got shocked. Some telegraph systems continued to operate on auroral currents alone after disconnecting batteries. If such an event struck today, studies suggest it could severely damage electric grids and satellites globally, potentially causing trillions in damages. A more recent case, March 1989, a strong CME hit Earth and caused a geomagnetic storm that collapsed Quebec's power grid within seconds. Millions lost power for hours, and some transformers were permanently damaged. In the same storm, auroras were seen as far south as Texas and Florida. Another event in Halloween 2003 caused less grid damage, but did affect satellites and caused a geomagnetic storm that disrupted parts of Sweden's grid and affected airline comms. And in 2005, a lesser-known storm still caused GPS outages for hours due to ionospheric disturbances. So, geomagnetic storms matter. They are rated by NOAA as G1 to G5 based on how much Earth's magnetic field deviates. G5 events are rare. The last truly extreme one was 2003's Halloween storm. During storms, auroras can be seen much farther from the poles than usual. People in mid-latitudes who rarely see them might get a treat. Red auroras overhead, green curtains on the horizon. It's often a surprise and delight. Historically, low-latitude auroras freaked people out. Besides auroras and power issues, geomagnetic storms can disturb navigation and create extra drag on low-orbit satellites by heating the upper atmosphere. We can often get some warning. Satellites like ACE or DSCO-VR at L1 measure the solar wind about 1 million miles upstream, giving us 30,060 minutes notice of the CME's magnetic orientation and velocity before it hits Earth. That helps alert power grid operators to prepare. Spacecraft can be put in safe mode to avoid damage from high-energy particles. Astronauts can take cover in shielded parts of the ISS. Airlines can reroute flights. These mitigations rely on us detecting the sun's storms soon after they start and monitoring the in situ wind. Now, not every solar storm hits Earth. The sun is blasting things out all the time in various directions. Earth, a small target, intersects only some. Sometimes we see a huge flare in CME, but it goes off to the side. Other times, a seemingly modest flare may send a CME squarely toward us and catch us head-on. Space weather forecasters analyze coronagraph images and measure CME speeds to predict arrival times. While the largest events are rare, even moderate storms can be disruptive. For example, the Halloween storms of 2003 caused 2 large geomagnetic storms, damaged or disrupted satellites, rerouted flights, and gave spectacular auroras. That was with sunspot cycle 23 near end. It's interesting that sometimes big flares don't produce proportionally big geostorms. It depends on the CME magnetic alignment. In 2012, a monster CME shot out, but missed Earth. In 2015, a strong CME's field wasn't southward, so it produced a milder storm than expected. Beyond Earth, solar storms can affect other planets too, of course. Mars,
lacking a strong global magnetosphere, gets walloped more directly. Its atmosphere gets eroded gradually by many CME hits. Jupiter's magnetic field responds with its own auroras and disturbances. Solar flares also have interesting effects. They can cause cosmic ray intensity to drop because the expanded solar wind and magnetic flux after a CME sweeps away some cosmic rays for a few days. One might wonder, could a solar flare or CME directly harm life on Earth's surface? Thanks to our atmosphere and magnetosphere, not really. Even the worst case solar particle storm might up the radiation slightly at ground level, but not enough to be lethal or cause immediate issues for humans. The risk is more to technology. Perhaps if a truly gigantic flare happened, you might see minor radiation effects at aircraft altitudes. But life has survived countless solar storms over billions of years. The sun's variability is modest enough that it hasn't sterilized Earth. For astronauts on Mars or future moon bases, though, these storms are a significant hazard outside of Earth's magnetic cradle. A big solar particle event can deliver a potentially lethal dose of radiation if astronauts are caught unprotected. This happened, fortunately in timing, in August 1972, a huge solar proton storm between Apollo 16 and 17 missions. Had astronauts been en route to the moon then, they could have been in serious danger. So space agencies plan to have shelters and storm forecasts for deep space missions. The interplay of flares, CMEs, and cosmic rays also extends to potentially affecting Earth's clouds or climate slightly. There's an interesting possible link. During strong solar activity, cosmic rays are reduced, and some scientists speculated that fewer cosmic rays mean fewer cloud seeds. Thus, in times of high solar activity, maybe slightly less cloud cover and a tad more warming, and vice versa. This theory is still debated. Evidence isn't very strong that cosmic ray changes make large climate differences, but it's an intriguing idea connecting solar magnetism to weather. In summary, solar storms are the climax of the sun's magnetic drama. They turn the sun from a steady light into an occasional threat. For much of history, humans noticed their side effects only as awe-inspiring auroras or disrupted telegraphs. Today, in our interconnected, electrified world, we watch the sun closely because a big storm could mean days without power or lost satellites. It's fascinating and a little unsettling that our mild-looking sun can flex such power across space. At the same time, these storms have likely been occurring for eons, and life persisted. They may have even helped Earth's atmosphere over geological time by providing energy for chemical reactions or by injecting atmospheric nitrogen oxides. On some level, they remind us the sun is not a static lamp, but a star, and all stars have tempests. The sun and Earth, a delicate balance. Despite the sun's occasional violence, it is indisputable that without it, Earth would be lifeless. The sun sits at just the right distance to make Earth a comfortable habitat. The sun sustains life in every way. It provides virtually all the energy that drives Earth's climate and ecosystems. If the sun's light stopped for even a week, Earth would plunge into deep freeze and most life would perish shortly after. Let's walk through the many threads of connection between the sun and life. Photosynthesis, the basis of the food chain. Plants, algae, and cyanobacteria capture sunlight and use its energy to turn carbon dioxide and water into sugars and oxygen. This process, which has been ongoing for 2-3 billion years, created the oxygen-rich atmosphere we breathe and feeds almost all organisms directly or indirectly. When you eat a piece of bread or fruit, you're consuming stored sunshine, the plant that made it packaged solar energy into a chemical form. Even fossil fuels are ancient sunlight. Coal, oil, and gas are the remains of plants and plankton from hundreds of millions of years ago who used sunlight to grow. Burning those fuels releases that solar energy that was stored long ago. Thus, quite literally, all life is sunlight, slowed down and transformed.
A poetic but true statement. We are all made of sunshine. The calories you burn with each breath were gathered by a plant from the sun. If the sun had not shone, Earth might have some chemical energy life at deep-sea vents, but likely nothing like the thriving biosphere we know. Climate and weather. The sun's energy drives the circulation of our atmosphere and oceans. The equator gets more direct sunlight than the poles, creating temperature gradients. Warm air rises at the equator, flows toward poles, cools and sinks, setting up convection cells that produce prevailing winds and weather patterns. The rotation of Earth and the distribution of continents complicate it, but fundamentally, wind exists because the sun heats some parts of Earth more than others. The water cycle, evaporation, cloud formation, rain, rivers flowing, is powered by solar heating of the oceans and land. No sunlight, no evaporation, no rain. The sun lifts water vapor up, which then condenses and falls as precipitation, enabling terrestrial life and shaping landscapes. Day-night rhythms. The daily cycle of light and dark has imprinted itself on life's behavior and physiology. Almost all organisms have circadian rhythms, internal clocks attuned to the 24-hour cycle of light and darkness. Humans get sleepy after sunset because our pineal gland produces melatonin in the dark. Sunlight each morning resets our circadian clock, syncing our sleep-wake with the outside world. Plants orient their leaves or open their flowers with the sun. Animals might be nocturnal or diurnal, depending on how they've adapted to the presence or absence of light. Before artificial light, human activity was largely diurnal. We did things in daylight and rested at night. Even now, many of us find bright light at night disruptive and a sunny day energizing, which is a deep evolutionary wiring. Seasons. Earth's axial tilt means the sun's angle changes over the year, giving seasons. In winter, less sun and lower angle leads to cold. In summer, more sun and higher angle leads to warmth. Life evolved strategies to cope. Deciduous trees shed leaves in temperate winter to avoid frost damage when sunlight is too weak to support them. Animals hibernate or migrate to follow the sun's warmth. Crop planting cycles align with seasons. Civilizations developed calendars to predict solstices and equinoxes. These allowed planning of agriculture and festivals. Many cultures celebrated the winter solstice as a time of rebirth and hope. Indeed, our modern holidays like Christmas align with ancient solstice festivals like Saturnalia or Yule, essentially celebrations of the sun's return. Psychological impact. The sun and its light have a direct effect on mood. Winter blues, or seasonal affective disorder, is a depression that hits some people in dark winter months. It's linked to lower sunlight causing changes in brain chemistry. Treatment often includes light therapy, essentially giving people artificial sunlight to cheer up their brains. We use sunny metaphors for happiness and dark for sadness, which shows a universal intuition. Sunlight correlates with positive feelings, darkness with gloom. Physical health. Sunlight triggers the production of vitamin D in human skin, which is essential for bone health and immune function. Historically, societies in low sunlight regions had diets to compensate to avoid rickets. Conversely, too much sun can cause skin damage or cancer. So there's a balance organisms must strike between harnessing the sun and being harmed by it. Sunlight also helps regulate various bodily functions, from sleep cycles to potentially blood pressure. Moderate sun exposure tends to correlate with certain health benefits, whereas none, or too much, have downsides. Oceans and currents. Sun warms equatorial waters more than polar. That drives global ocean currents. These currents shape climates. The sun's uneven heating of Earth thus orchestrates even these deep ocean patterns. Extreme dependence. Virtually nothing on Earth is untouched by the sun. Even cave ecosystems that never see sunlight ultimately rely on energy that originally came from the surface.
Only some rare ecosystems like deep-sea vents might circumvent the sun by using Earth's internal heat and chemistry as an energy source, interestingly giving us clues how life could exist on sunless worlds like Europa's ocean or under Titan's crust. But those are exceptions. The bounty and complexity of life we know is thanks to the sun's abundant energy pouring down. Protective shields. The sun's magnetic field, via the solar wind, also helps shield the inner solar system from some cosmic rays. Earth's magnetic field, in turn, shields us from much of the solar wind. It's like layers of defense. Earth's magnetosphere and atmosphere protect life from most harmful space radiation. Without the sun's stable output and Earth's shielding, life on land would be very different or impossible. The far future. The sun won't always be so kind. In about 1 billion years, as it brightens, Earth might get too hot for comfort. That would be a slow, moving disaster, though. Later, in 5 billion years, the sun will expand to a red giant and likely end the Earth as we know it. But by then, maybe our descendants will have migrated elsewhere or adapted in ways we can't imagine. It's worth noting that while the sun's output is currently steady, even small changes have been linked to climate shifts historically. The sun might have influenced Earth's climate slightly over centuries. Now, human factors are overpowering such subtle solar changes. Beyond physics and biology, the sun influenced culture and religion profoundly, as covered earlier. Rulers aligned themselves with the sun. Ancient Egyptians had a whole theology around the sun's cycle. The Japanese emperor was believed to descend from Amaterasu, the sun goddess. The sun was a universal symbol for life, energy, and rebirth. Even today, in language, we have vestiges. Sunday, literally Sun's Day. Many national flags have suns. We celebrate things like the summer solstice in festivals. Science gave us a more factual, less mystical sun, but we still greet a sunny morning with a certain joy. So the balance is, the sun gives us life and sometimes threatens it, but mostly sustains. Earth has been lucky to have a star of just the right mass. More massive stars burn out too fast. Less massive ones might be too fickle, or have planets too close and tidally locked. Our sun is indeed a fairly ordinary star, but for us, it is extraordinary, the one and only source of light and life. Astronauts orbiting Earth often remark on the stunning view of the sun cresting our blue atmosphere, sometimes calling it a fragile layer protecting us. If you watch an orbital sunrise from the ISS, you see a bright point intensify, and then a blazing star burst over the horizon with a jewel, like thin blue line beneath, a visceral reminder of how dependent we are on that light, and on that tenuous air to moderate it for us. We live in the sun's extended atmosphere. We eat its light. We feel its warmth. We fear its storms, and we bask in its glory. That relationship has defined Earth's story from the very beginning. Life's emergence, evolution, and ultimately maybe life's end here when the sun changes state. To put it succinctly, if Earth is our mother, then the sun is our father, providing the energy of life. Both are needed, and indeed many cultures personified them that way. Even going beyond Earth, when we search for habitable exoplanets, we're basically hunting for other Earths around other suns. The conditions that make Earth habitable revolve around having a star like the sun at the right distance, plus Earth's own attributes. We basically look for similar star-planet arrangements because we recognize how fundamental the star's role is. In closing this segment, every warm breeze, every raindrop, every green leaf, every breath of oxygen, every shimmering aurora, all trace back to our sun. It's truly the heart of our existence. The Earth-Sun connection is intimate and profound. Understanding that scientifically doesn't diminish its wonder, it enhances it, as we see even more clearly how finely tuned and interwoven the system is. The sun's living past and future. We've journeyed through the sun's present workings, but the sun's story has a timeline, a biography from birth to death, with Earth riding along for part of the way. Let's step back to understand where our sun came from and where it is going, and how that shapes the broader narrative of stars and life. Birth recap. Our sun ignited about 4.6 billion years ago, likely in a cluster with siblings. We see evidence of a nearby supernova explosion around the time of the sun's birth. Certain isotopes in meteorites suggest that a supernova shockwave might have triggered the collapse of the molecular cloud that formed our solar system. So perhaps a massive star's death helped spark the sun's birth. In that cloud, not just the sun, but other stars would have formed. We find some solar sibling candidates by chemistry and motion in the galaxy, but over 4+ billion years, the cluster dispersed. As a young star, the sun was likely more active. Young suns spin faster and have more flares, strong winds. There's evidence Earth's early atmosphere experienced intense solar winds and flares. But fortunately, by the time life arose, the sun had probably calmed to a more stable state, though still a bit dimmer than today. The faint young sun paradox. Astrophysical models say the sun was 30%. The response is very long and presumably covers all points requested.